Everybody ready? Okay, let's get started. We're going to continue what we started yesterday. We'll talk about prefetching today. Yesterday, we actually did talk about prefetching also. It was a different kind of prefetching. Prefetching is a method of latency tolerance or latency reduction from the processor's perspective, not necessarily from the memory's perspective, right? You still have the full latency, but you're really tolerating that latency by bringing the stuff earlier into somewhere. That's what run-ahead execution did. It did it in a very accurate way, but we're going to cover a lot of other methods for prefetching today. Okay, so this is just a quick reminder of what we covered yesterday: latency tolerance, run-ahead, and we talked a lot about wrong path effects, which is really interesting. Today is mainly dedicated to prefetching, but I would like to take the last 10 minutes to talk about the exam. Okay, we'll do it at the end. Okay, let's jump into prefetching. This is an outline. I think it's not going to be lectures. It's going to be a lecture since we didn't really start it yesterday, and we have enough time, I think, to cover everything over here. This is another topic that has fascinated a lot of people. Again, this is not just a processor-specific topic. Today's operating systems do a lot of prefetching. They try to guess what the user is going to touch next in memory or in terms of files, and they try to preload that into the memory system. In fact, Windows has very sophisticated machine learning-based prefetchers that try to figure out at what time of day what application you're going to load and what do you think you're going to need, right? That's done in operating systems. It's done in web servers. They do a lot of prefetching. It's done in web. They do a lot of prefetching. So whenever you're actually browsing some web page, your web browsers are actually prefetching stuff, expecting that you're going to click on the links that are on the web page. That's a form of content-directed prefetching, actually, which we're going to see in the context of computer architecture also. They look at the content of the web page, a bunch of links. Maybe some of them are popular links. They can learn that information, and they prefetch them to the cache of the browser, right? So it's a very general idea, preload data. I didn't define prefetching, but it's obvious. You preload the data. You load the data before you need it. It's a form of speculation, essentially. And in all kinds of prefetchers, regardless of whatever prefetcher you're designing in any part of the system, high level, low level, hardware, there are always 4 questions. What do you prefetch? When do you prefetch? Where do you prefetch it to? And how do you do it? Right. And we're going to talk about those 4 questions. And again, you can do it in software. You could do it in hardware. You could do it execution-based, which could be software or hardware, actually, or cooperative. And in all prefetchers, you have performance metrics: coverage, accuracy, timeliness. They're all important, and you trade off between them usually. Usually you cannot get all of them at the same time. And also there are some other metrics that affect other things, like bandwidth consumption, cache pollution. Of course, energy is affected by a lot of these. And we'll talk about prefetcher throttling. All prefetchers actually are throttled today in some way to ensure that you're achieving some good. And hopefully we will get to issues in multi-core. Okay, these are some readings. Although I say they're required, they're not really required until we require them. But it's good for you to read them, of course. And these are some recommended readings also. Okay, and just also, you're already reading this anyway. Okay, so the idea is very simple. Fetch the data before you need it, right? That's why it's called prefetch. It's also called preloading, before you really need to load. Why do we want to do it? As we've discussed, memory latency is high. If we can prefetch accurately and early enough, we can reduce or eliminate that latency from the processor's perspective, from the computational unit's perspective, basically. And it can eliminate compulsory cache misses, basically. Things that you can be proactive about prefetching, right? Even if you have never seen an address before, you can get it, right? The thing I described earlier, content-directed prefetching from a web page, is actually proactive, right? You may never have clicked on that link before, but based on other information, it prefetches that link, those pages for you. Okay, one question that immediately comes up is, can we eliminate all cache misses, capacity conflict? What do you think the answer would be? If you're perfect at prefetching, there's no reason not to, right? You could actually eliminate all cache misses. And people actually propose ideas. Some of these we're not going to cover necessarily, but if you have a speculative version of the program, think run-ahead execution right now, if you have 2 cores, one core is very speculative, you prune the program, it's just for prefetching, it executes on that core, and the other core is just real, doing things for real. If you actually have these 2 cores coupled together, one core is prefetching for the previous one who is doing the real work. Maybe you eliminate all the cache misses for the core that's doing the real work, right? This is called slipstream processing. Basically, if you think about, are any of you car racers? I'm not one. But if you're in Formula One or these high-speed car racing, cars actually get close to each other so that they can actually block the wind, and they can go faster together if they're close to each other because of the wind effects. So the slipstream is kind of similar to that. That's called the slipstream effect, essentially. You're ensuring that by prefetching early, you're ensuring that this thing is not stalling because of the wind, which may be the memory latency. And you're going fast because you need to execute a pruned version of the program to prefetch. And the other program, the main program, is going fast because you're prefetching for it. Right? Basically, the 2 cores are slipstreaming, or 2 threads are slipstreaming, such that they can overall execute the program much faster. So I can put a link to that paper, Slipstream Execution. But we're not going to cover that. If we have time, we'll get into it. So I could actually play a lot of interesting tricks with multi-threading. That's one form of prefetching. So I'd like you to get the broader picture. That's why I mentioned that. So we're going to start with simpler prefetchers, of course. So clearly, this involves predicting which address will be needed in the future. And this works if programs have predictable misaddress patterns, especially with simpler prefetchers. What I described, Slipstream, is not implemented in existing systems because of its complexity, partially because there are a lot of research questions related to it also. But some other things where you have predictable misaddress patterns are implemented in existing systems. Okay, so one question is prefetching and correctness. We covered this yesterday in the context of run-ahead execution, right? One of the reasons why run-ahead execution is very appealing is in this mode, you can do anything, basically, because you're not reporting the results to the software. That's true for prefetching in general. A misprediction in prefetching doesn't affect correctness. You're just loading an address, and you're not going to do anything with it if you're incorrect. Basically, prefetch data at a mispredicted address or wrong address that you're not going to use is simply not used, basically. There's no need for state recovery. This is very different from branch prediction. And if you mispredicted the branch, you have to correct your action, right? Otherwise, you'll be on the wrong path for a long time. Well, you will never recover, basically. That's true for value misprediction also, except for unless you do these in this always in speculative mode. Okay, so we can actually have a lot of leeway here. We could prefetch random addresses. Of course, that may not be good for performance, but you could do that, right? Okay, so in modern systems, prefetching is usually done in a cache block granularity because things operate in the granularity of cache blocks. And it's a technique that can reduce both miss rate and miss latency. So if you prefetch early enough, the thing that you prefetch, the block you prefetch is already in the cache or in a prefetch buffer. We'll talk about where. So you get rid of you reduce the miss rate. You eliminate some misses. But you may prefetch, and then soon after that, the processor may demand that address. At that point, when the miss buffers, you merge those requests, right? Remember the miss status handling registers. You reduce the miss latency that's observed by the load that needs the request, but you don't reduce the miss rate in that case, right? Because the prefetch is in that case a little bit late, if you will. If you had prefetched it early enough, you would have reduced the miss rate, but you prefetched it a little bit late, you reduce the miss latency. Of course, it's a continuum, right? You can reduce 1 cycle, 2 cycle, 5 cycle, 10 cycles, 100 cycles, and if you reduce all of the cycles, then you impact the miss rate. And it's obvious, hopefully, prefetching can be done by many entities, hardware, compiler, programmer, in the context of what we're going to examine, but of course at the operating system or server, web server level as well, too. Okay, this is one example. This is actually a relatively old picture, but I just want to give you how a prefetcher fits in the memory system. This is a memory system, and you can see that it's a bit old because the memory control is on the other side of the bus. It used to be that way a while back, but it doesn't change things over here. Usually, in today's systems, you have prefetchers at multiple levels, but this is one example level where the prefetcher can be effective. Basically, in this case, you have a stream prefetcher. It observes the requests that are coming into the L2 cache, and trains the streams in different ways, as we will talk about. And it also observes what misses in the L2 cache so that it can create some streams, in this case. And based on that information, it inserts some prefetches into the request queue. And then those requests access the L2 cache. If they miss, they generate prefetches that get serviced. Right? That's one example. And you can have prefetchers over here. You can have prefetchers in the memory controller. And existing systems actually have prefetchers everywhere because this is such a memory latency is such a big issue. And one of the issues, of course, is how do you coordinate those prefetchers across the levels. And there are cores that are having different prefetchers as well. How do you coordinate between those cores? Hopefully, we'll get to that as well. OK, so these are the 4 fundamental questions in any kind of prefetching system. What addresses do you prefetch? When do you initiate a prefetch request? Where to place the prefetch data? And how to do it? What is the algorithm? Do you do it in software, hardware, execution-based, or cooperative? We're going to look at all of these quickly first. So what addresses to prefetch? Clearly, prefetching useless data wastes resources. It doesn't affect correctness, but it wastes resources, memory bandwidth, cache space, or prefetch buffer space, depending on where you put it, energy consumption. And those resources can all be utilized by demand requests or more accurate prefetch requests. So they cause interference as well, if you don't do the prefetching well. An accurate prediction of addresses to prefetch is very important. And prefetch accuracy is the one fundamental metric, which is very simply, how many prefetches did you send? Well, how many prefetches did you use out of the ones you've sent, divided by how many prefetches did you send? Simple, right? It's not the only metric. So the key question is, how do we know what to prefetch? Right? So we can predict based on past access patterns, use the compiler's knowledge of the data structures. We're going to see different techniques. In run-ahead execution, you saw how we knew what to prefetch, right? We basically pre-executed the program. That's one way of doing prefetching. So prefetching algorithm determines what to prefetch. So since you know about run-ahead execution, the algorithm in run-ahead execution was to execute the program and handle the valid and invalid data. But prefetching algorithms vary very widely. OK, let's go to when. When do you initiate a prefetch request? This is important because it affects timeliness, essentially. If you prefetch too early, the prefetch data may be evicted from the structure that you put it into before it's used. Right? Even if it's accurate, it may not be timely enough or late enough in this case. Right? So you've done it too early, basically. As a result, it causes waste. Prefetching too late is also bad because it may not hide the whole memory latency, right? It may not reduce your miss rate. Ideally, you would like to prefetch just enough ahead such that you don't incur any delay when the load executes, right? So maybe one cycle before the load executes, the data comes back. The prefetch data comes back. Of course, this is very difficult to time in real life, right? There are so many dynamic events that are going on in the system. But it's important to strive for prefetching just in time. And when a data item is prefetched, affect the timeliness. This is called the timeliness. Timeliness is a harder to define metric. People have tried to define metrics for it, but we're not going to deal with that right now. Prefetcher can be, of course, made more timely by making it more aggressive. Right? You can try to stay far ahead of the processor's access stream. So if the processor is, let's say, a very simple pattern, it's called streaming if you're accessing consecutive addresses, n plus 1, n plus 2, n plus 3. If you figure out that you're not timely, maybe you prefetch 32 blocks ahead of the processor's access stream. Right? Whenever the processor accesses block n, you prefetch block n plus 32 in anticipation that the processor will get to n plus 32 by doing the streaming behavior. Right? So you always stay ahead. Now, of course, the downside of this could be you may be wrong, right? You're always prefetching 32 cache blocks ahead, and the processor at some point stops going through the streaming behavior, so you wasted a lot of things that you prefetched because the processor is not going to touch them. Right? That's a fundamental trade-off between accuracy and timeliness, actually. You may increase timeliness at the expense of accuracy. And if you're doing the prefetching in the software, which we will see, you may move the prefetch instructions earlier in the code. So you may have explicit instructions that said prefetch this data. And the compiler may know the access pattern, so it can actually schedule those prefetch instructions early enough in the code. But if it puts it too early, maybe it runs into this problem. And also, it may run into the accuracy problem also, right? because if it puts the instructions too early, maybe you actually prefetch some things, and there will be a branch that's taken in some other way, and the program will not access it, right? Okay. So hopefully these are relatively simple. So where to prefetch the data is also important. You can put it inside the cache, which is what most modern processors actually do, or you can put it inside a separate prefetch buffer. If you put it inside the cache, the design is simple. There's no need for a separate buffer. If you actually work on the memory hierarchy, which you will do in your lab 4, you will figure out that things can get complicated very quickly. Adding more buffers actually adds complexity into the system. So this is good because it keeps things simple. And all of the paths already exist, right? All of the interconnect already exists to bring data into the caches. Now the downside is now you can evict useful demand data. You cause cache pollution. So basically more contention in the cache. And all of the issues that we've discussed with caching becomes exacerbated because now you're putting prefetches into that also. And prefetches may have different reuse behavior, as we will hopefully get to compared to demands. Or you could place it into a separate prefetch buffer. Now the demand data is protected from prefetches, no cache pollution to the demand data. But of course, now you have many, many other choices. I just want to give you the effect on the complexity. This doesn't mean that it's a bad idea just because I've listed a laundry list over here. So where to place the prefetch buffer becomes a problem. Do you place it with L1 cache, L2 cache? Do you have a prefetch buffer at LE level? I don't know. When do you access the prefetch buffer? Do you access in parallel versus serial with the cache? Design choice. When do you move the data from the prefetch buffer into the cache, if you ever do so? How to size the prefetch buffer? In fact, if you size it too little, and if you have an aggressive prefetcher, you might as well not have the prefetch buffer. There are a lot of results that show that, actually. And keeping the prefetch buffer coherent is another issue, right? You prefetch the data, but somebody else updated that data. You should not provide the wrong data to the processor. Right? So there are a lot of design complexity issues with another buffer that's added to the memory system. And as a result of this, many modern systems just prefetch data into the cache because it just keeps things simple. Okay, these are old processors, but you could extend it over here. Okay, anything else I want to say about this? Probably not. Any questions? Let me cover the fourth question also. Well, where actually has multiple things. Where to place, and also which level of cache, and also where in the cache. So this is actually important. Do you assuming L2 is the last level cache, you can extend it to any levels, but do you prefetch from memory to L2 only, or directly from memory to L1? What are the advantages and disadvantages? So if you're actually prefetching into the cache, if your L1 is small, maybe you don't want to prefetch into that. Maybe you want to have a really judicious prefetcher that prefetches very, very carefully into L1. But L2, if it's huge, or L3, if it's huge, there are a lot of blocks that are dead in that cache anyway. Having more aggressive prefetchers put blocks into the L2, L3 big caches may not be as big of a problem. Right? And of course, this now begs the question, maybe you should design separate prefetchers from L3 to, from memory to L3, L3 to L2, L2 to L1. And actually, that's what's designed in a lot of high-performance processors today. There is even a prefetcher in the memory controller that tries to prefetch into buffers over there. Okay. We're not going to cover all of that detail, of course. But even if you prefetch into the cache, now you have a choice of where to place the data into the cache. Right? Do we treat prefetch blocks the same as demand fetch blocks? The answer is usually no, but many processors actually do treat them the same way. As a result, they run into problems in caching efficiency. And I will show you why the answer is no. Although that's not true. So, for example, in HPPA, I think this was 8000, what they did was they prefetched the data into the LRU position in a large last-level cache. So they expected that the prefetch data is either going to be used very quickly after prefetching or not going to be used. As a result, they put the prefetch block into the LRU position. So this minimizes the impact of prefetching on all of the other ways in the cache. Right? Okay. And prefetch blocks are not known to be needed. With LRU, a demand block is placed into the MRU position, most recently used position. Then the key question is, do we skew the replacement policy and insertion policy such that it favors the demand fetch blocks. For example, what I just discussed, place all the prefetches into the LRU position in a way. That turns out that's not also the best, because if you really have a good, accurate, and very timely or early prefetcher, now if you place the prefetch into the LRU position, that prefetch can get evicted really quickly, right, if there is a conflict from a demand. So you really need to take into account the accuracy of the prefetcher and a bunch of other metrics, and we'll talk about prefetcher throttling. Okay, so where is a little bit complicated, as you can see. Well, there's more, actually. where to place the hardware prefetcher in the memory hierarchy, which is similar to this one, actually, but not necessarily exactly the same, because you may place the hardware prefetcher somewhere, and that hardware prefetcher sees some misses or accesses, and it may prefetch into some other level. So you can, for example, have a memory prefetcher in the memory controller prefetching directly into the L1 cache. It's possible. But basically, this determines where you place the hardware prefetcher determines what access patterns the prefetcher sees. So in the picture that I showed you, it was seeing the access pattern that goes into the L2 cache. Right? That's very different from the access pattern that goes into the L1 cache. L1 hits don't get exposed to a prefetcher that sits in front of the L2 cache. Right? So you get a filtered access pattern, which means that you may actually miss some of the patterns in the processor's full access stream. That may or may not be good. So if you see a more complete access pattern, if you're seeing every single request that is made by the processor, you potentially can get better accuracy and coverage because you can analyze that access pattern better. Now the downside is the prefetcher needs to examine many more requests, right? Every single load or store now goes to the prefetcher. But if you see a less complete access pattern, you can make the prefetcher simpler, but you may actually lose accuracy and coverage because you don't see everything that the processor demands. In fact, some of them may be, even though a processor may have a very regular access stream, you may see irregularity in the later parts because there might be other processors that are contending in the cache with that processor and kicking out things from the cache. As a result, the prefetcher that sits farther away from the processor may see maybe a random access stream. I don't know. Okay, any questions? This is the fourth question. Now we're in the fourth question. Fourth question is actually very broad. How do you do the prefetching? Otherwise, how you do the prefetching, because how can actually describe everything else we've described also. But given that you made all of the other things, other decisions, how do you do the prefetching? Do you do software prefetching? In which case, the ISA provides prefetch instructions, and the programmer or the compiler inserts prefetch instructions, which clearly require some effort from the software's part. And this usually works well for regular access patterns, but once your patterns become irregular, it becomes difficult. Hardware prefetching, hardware monitors the processor accesses, or also not only regular, but also statically determinable or profilable, and we'll see that. Hardware monitors the processor accesses in this case, and memorizes or finds patterns or strides, and generates the prefetch address automatically. And this usually works better for regular access patterns, but some irregularity can be possible also here. Execution-based prefetchers essentially execute a thread to prefetch the data for the main program. So run-it execution is one example of this, as we've discussed yesterday. That thread is created by the hardware dynamically when you stall, when the oldest instruction is a long latency cache miss. What I described earlier, the slipstream execution, is essentially a form of execution-based prefetcher. Somebody creates this thread that runs on a different core whose sole function is prefetching for the main program. And this thread actually can be generated by either software and the programmer, compiler again, or hardware again. So we'll see this as well. I think this is fascinating, and clearly you can combine all of these, and existing systems actually combine all of these. Then there's another question, right? How do you coordinate between all of these prefetches? That's a very interesting control problem too. This is where machine learning can help too. There are places where machine learning can actually help the design significantly. Okay, let's jump into the first one. This is software prefetching. The idea is very simple. compiler or the programmer places prefetch instructions into appropriate places in the code, right? And this is, there are multiple concurrent papers. This is one of the papers that show positive results. Actually, one of the earlier papers shows negative results from software prefetching. Maybe the prefetches were not inserted very well, but they're all good papers. Basically, you have prefetch instructions that prefetch data into caches in this case. Again, that's one design, right? You could have prefetch instructions that prefetch data into prefetch buffers, but that's not necessarily the case in this design. And the compiler or programmer can insert such instructions into the program. And these instructions exist. This is one piece, basically one page from the x86 manual, which is old. I'm sure this has changed because the definition of this is really microarchitecture dependent. So these are the prefetch instructions in x86. T0, that's for temporal data. And they say prefetch data into all levels of the cache hierarchy. And you give it an address, basically. And the specification is microarchitecture dependent. As you can see, basically in Pentium 3 processor, first or second level cache. As you can see, you don't get guarantees, right? Actually, you may be lucky if that's true also. I don't know. That happens, right? Pentium, because these are optional almost, right? These don't affect correctness of the processor. As a result, if the hardware designer is really tight on time, you know what happens to the optional features. You know that with the extra credits that you're doing, probably. Okay. So Pentium 4 and Intel Xeon processors, they say it's to the second level cache. So they don't want to pollute even the first level cache with the software prefetch instructions, as you can see over here. Right? Because first level cache space is so precious. Okay, and there's also T1, there's also T2. As you can see, temporal data with respect to the first level cache, they don't place it into the first level cache. Temporal data with respect to the second level cache. It's interesting because it's not clear what this exactly means because the behavior is specified to be exactly the same. This is old also, so there might be new definitions clearly. As you can see, this talks about Pentium 3, Pentium 4. And this is non-temporal. This is also interesting, I think. Basically, they bring this non-temporal data into a location close to the processor, and they don't bring it to the other levels. Again, that's what the specification says. If you really want to know how it works, you really need to reverse engineer what's going on in the hardware. Or look at a manual that actually has done that already. Okay. So what is software prefetching? Basically, you can insert pragmas in the programming language like this, right? This is one pragma that I just came up with. What this is doing is this basically this is a very regular access pattern, as you can see. You even may know the loop bound over here. But it's clear that you're streaming through both of these arrays. And I inserted prefetch instructions to 8 iterations ahead. So this iteration prefetches for 8 iterations ahead in this case. And this can work very well for regular array-based access patterns that look like this, right? Now, how do you determine how far ahead do you prefetch? That's the difficulty. Well, that's one of the difficulties, right? And we'll get to that. But there are other difficulties. So this is a prefetch instruction. It doesn't stall the processor, so that's good. A good prefetch instruction should not stall the processor. Because if it stalls, then it becomes a load, right? That's bad. So it's a non-blocking instruction. But they take up processing and execution bandwidth. So they need to go through the pipeline until they are executed. So that's one downside. How early to prefetch becomes a problem, determining this difficult. How do you actually decide you do 8 iterations ahead? Why not 2 iterations ahead? Why not 16 iterations ahead? Right? Why not pull some of these? Why not have another loop over here that just prefetching? Right? You could do that also. It's possible. And actually compilers do that. But the difficulty is, how far ahead do you do it? Now this is dependent on your memory latency, cache access patterns. Clearly, how much work do you do in a loop? And usually there's an equation that you use in the compiler to estimate all of that. Right? So if your memory latency is constant, let's say 100 cycles, and you do 5 cycles of work in each loop iteration, you should be prefetching 20 loop iterations ahead. Right? But of course, life is not that beautiful. You don't know all of those magic values. Okay. So prefetch distance clearly depends on so this is called prefetch distance, how far ahead you prefetch. In this case, the prefetch distance is 8 iterations ahead, or 8 blocks ahead because it's a regular prefetch, regular access pattern. But that distance depends on many things. Hardware implementation, like memory latency, cache size, cache associativity, how long it takes to execute the loop iteration. And all of them are dependent on the microarchitecture, which means that if you insert these prefetches for some microarchitecture, and if you run the program on some other microarchitecture, you may actually lose performance. And that happens. If you insert these prefetches, you can insert these prefetches based on program analysis. You don't need to profile. But there may be some more complicated access patterns where life is not that nice. You profile the program and you try to figure out the access pattern. And based on that, you insert the prefetches. Now your prefetches are profile dependent. Right? So if your input data changes when you run, you may lose performance again. Right? So this is not so adaptive to changes in the execution environment, as well as the input data into the program. So that's always been a problem with software prefetching. But if you can actually do it, it's actually very powerful. So going too far back in the code reduces accuracy. So in this case, for example, you will prefetch 8 iterations ahead even after you exit the loop, right? So how do you prevent things like that? So you will waste bandwidth if you do it this way. Now, if you don't do it this way, then you may actually have other overheads. That's why actually putting it out of the loop might be good, right? Okay, but once you start putting it out of the loop, putting it ahead, if the prefetch goes here, and if there's a branch in between, now the probability that you're going to use the prefetch data starts reducing, right? As you keep going earlier in the program, the probability of use of the prefetch, i.e. accuracy, reduces. Okay, and do you need special prefetch instructions in the ISA? Not necessarily, actually. Alpha ISA, for example, used a load instruction. If the load's destination register was register 31, that was treated as a prefetch. Why? Because they hardwired the register 31 to be 0. By definition, you could not change register 31. So it's nice. You could use tricks like that. PowerPC has the data cache block touch instruction, and we saw x86. So all major ISAs have prefetch instructions. So this is how it's done today, but in the future, there might be other prefetch instructions. Maybe the prefetch doesn't exactly specify what to do, but it informs a hardware structure, and it gives a hint to the hardware structure. Look, your stride is probably 8 over here. So whenever you see this access, start striding with 8. So that's a hint, right? This now encodes a prefetch. You should prefetch this address. But if you want to be more flexible, maybe you might want to give a hint to some other structure that is aware of the dynamic execution environment. Now you're tying yourself much less to a specific hardware implementation. Right? Okay, so these are actually things that are in progress. So this is one other disadvantage. It's not easy to do for irregular access patterns in general, and statically not predictable access patterns in general, but pointer-based data structures in particular. Right? Let's take a look at this. So this is a pointer based traversal. As we've seen, it's a linked list traversal. So what this is trying to do is to prefetch the next node address, right? Now you can do this, it's nice. But maybe you want to prefetch ahead. Maybe you want to prefetch, I don't know, 8th next node, right? How do you do that? Or 3rd next node? Well, maybe you do this. Of course this doesn't work. Right? Because now you have a serial dependence. You need to load this p next to load the next pointer to load the next pointer. Now you created a blocking prefetch instruction, and you're back to square one. Right? So that's the problem. So how do you actually do this? That's actually difficult. These structures are very difficult to prefetch in the software level. But we'll see some execution-based prefetchers. You need to maybe keep some metadata. So one way of accomplishing this is actually when you traverse the list, you create... do you guys know about skip lists? What's a skip list? Data structure? Okay, maybe we should switch to this quickly. I didn't intend to talk about skip lists, but how do we do that? PC2. Okay, thanks. It's connected. So skip list is actually a software construct to enable fast traversal. So this is a linked list. In a linked list, you have pointers to the next node, right? You cannot see? Oh, okay. How do you autofocus? That one. It's what? Oh, there you go. It's doing something. Oh. It feels like some living structure. How do I block? How do I stop it? Lock it. There was a lock. Okay. I don't want to lock that one. Okay. This requires multiple people to operate. Amazing. So how do I zoom into this? Okay. What do you guys think? That doesn't look good. Oh, this is the lock I see. But how do I zoom? Oh, A3. Oh. Okay, only 3. Oh, you found something? Maybe. Okay, maybe I keep writing and I'll find something. Let's hope that. You guys can see this, right? No, I don't think. Okay, that's good. So this is a linked list. Clearly we have a pointer, right? One pointer. Is it still doing that? Amazing. It doesn't matter if you lock, actually. It goes back. This worked before. Okay. Okay, a skip list. Let's hope that this works. A skip list basically provides not just an X pointer, but you have another pointer over here that skips. And yeah, I don't have enough space over here. But in software, you can use that pointer to traverse much faster, right? And people have shown that you can actually find the item that you're looking for much faster by making use of these skip pointers. Now you can imagine adding those pointers into hardware also. Not hardware, in a software prefetcher. You create those pointers, even though your list may not be a skip list, you create those pointers in software and you use them for prefetching. So if you already have those pointers, use them for prefetching is one good idea, right? So now you can, when you're traversing this node, when the loop iteration is accessing, doing something here, you prefetch for this node m+3. Okay? We'll need to figure this out because I'm going to use this for something else also. But I don't know how to figure it out. Okay. Okay, now you learned about skip lists, although sorry about this thing. But it's a very powerful data structure. Okay, so which one is better over here? The answer is they're the same, I think. Because you're not gaining anything. Actually, you may be doing a lot more work over here. Okay, software prefetching, basically, where should a compiler insert prefetches? That question is hard, as we saw. Do you prefetch for every load access? It's too bandwidth intensive, because it consumes both memory and execution bandwidth. Do you profile the code and determine what loads are likely to miss? Maybe that's a good idea, right? But then what if your profile input set is not representative? I'm talking about in general right now, not specific access patterns, because if you have a really specific access pattern like this, then you may be able to play a lot of games there to make it work. But if it's more general, how do you know what instructions are going to miss in the cache, right? What if your profile input set is not representative? And how far ahead before the miss should the prefetch be inserted? Again, you can profile and determine the probability of use for various prefetch distances from the miss. So do I prefetch 8 iterations ahead, 16 iterations ahead, 24 iterations ahead? And you can decide a good one, but again, your profile input set may not be representative, right? And you usually need to insert a prefetch far in advance to cover hundreds of cycles of main memory latency, which reduces your accuracy. So this is not an easy problem, essentially. But people use it still. Especially in cases where you can analyze your program, you're in an execution environment where you ensure that their dynamic effects are minimized, then you can get the best out of it. Okay, let's take a look at the hardware side of it. Any questions with the software? Okay, the idea in hardware prefetching is we have a specialized hardware that observes load store access patterns and prefetches data based on the past access behavior. Now, this is not general enough. We'll see different kinds of prefetchers that do different things. Because it doesn't always have to be the past access behavior, but the simplest prefetchers are based on past access behavior. Now, there are trade-offs here. You can, the upside of this is you can tune this to system implementation, right? You're the hardware designer who's designing a particular microarchitecture. You know all the parameters associated with it, so you can design a hardware prefetcher that's customized for it. Of course, it's more effort, more complexity, but you can do it. And it doesn't waste instruction execution bandwidth. This is happening on the side while the program is executing, right? So a processor is not changed here, which is nice. Now, the downside is now you have more hardware complexity to detect patterns or do prefetching. Software can be more efficient in some cases, right? Like in the case we've seen, if you insert prefetch instruction in a very regular execution pattern, you don't waste hardware to try to figure out, oh, my stride is 1, 5, 7, ... Okay. So the simplest form of hardware prefetching is next-line prefetchers. These have been used since 1970s, actually. Even earlier than that, 1960s. The first use of prefetching was in the instruction prefetching of IBM 36091. They had a next-line prefetcher for the instruction engine. And the idea is you always prefetch the next cache line or next n cache lines, the generalized form of it, after a demand access or a demand miss. Again, when you trigger the prefetch is important. That's a design choice that we've discussed. So it's called the next line prefetcher or next sequential prefetcher, as it was called first. Even this has trade-offs. It's simple to implement clearly. There's no need for sophisticated pattern detection. By definition, it's assuming that you always, you're basically streaming through memory, right? It's good for instructions, clearly. Instructions, you may actually be doing this, except for control flow. And there's no need for sophisticated pattern detection. And it works well for the sequential streaming access patterns, instructions, but also some data. The array accesses that I showed you earlier, actually, that's streaming, right? Now, the downside is it can waste with irregular patterns. If you always do this, you're always prefetching something potentially useless, right? And even with regular patterns, right? If the prefetch accuracy, if the access stride is 2, you're doing address A plus 2, A plus 4, A plus 6. That's the demand access stream of the processor. But if you always prefetch the next one, then you have a problem, right? Your accuracy is 0 in that case. You're always prefetching the thing that you're not going to use. Now, if your access stride is 2, and if n is 2, your accuracy is 50%, but you got lucky. If your access stride is 3 and n is 2, again, you're back to 0%. So this is very inflexible, as you can see, right? And also, there's another issue. What if the program is traversing memory from higher to lower addresses? Which could happen. It was actually in one of the examples that I showed you yesterday, in the code example. One loop was going through the array backwards. The other loop was going through the array forwards, because it was actually partitioning the array into 2 and doing different operations. The 2 loops were doing the same operation on different parts. And you start from the pivot point that you partition the array. Yeah, so do you actually also prefetch the previous n cache lines? You do +1 and -1 at the same time, right? Yeah, so this becomes inflexible. So that's why people have developed stride prefetchers. There are 2 kinds of stride prefetchers. One is instruction program counter-based, and the second is cache block address-based, and there are some trade-offs associated with them. Let's take a look at what it is. Well, this is the paper that actually first proposed the instruction-based prefetcher. Basically, the idea is to record the distance between the memory addresses that is referenced by a load instruction, a given load instruction, the program counter. And that's the stride of the load, as well as the last address referenced by the load. That's it. If the load is always accessing address A plus 3, A plus 6, A plus 9, by just observing 2 consecutive executions of that load, you can determine the stride, and you can determine what to prefetch next. So next time you see the same load instruction, you prefetch the last address you've seen for that load plus the stride. Make sense? That's pretty simple, right? And you do it on a load base, because this paper showed that different loads have different strides, which may make sense also, right? Okay. So how do you actually build a predictor that looks like this? It's relatively simple. I'm not going to go through it in detail, but you index this with the program counter, tag You keep the last address that the load actually executed, the effective address, and you keep the last stride, and you may want to keep some confidence also, because the load may be doing address 8 plus 3, 8 plus 6, and then 8 plus 12, and then 8 plus 15. So there may be multiple strides, or they may not be a stride, but if you always look at the last stride, you may actually prefetch the wrong thing again, right? Okay? So there's a problem with this. So basically, whenever you fetch the load again, you look at the last address referenced, look up. If the stride is confident, you take that last address, add to it the stride, and generate a prefetch request. Right? So if the load is A plus 3, A plus 6, A plus 9, then this works nicely. Now, but there's one problem with this, which is the look-ahead problem. The prefetcher may not get very far ahead of the demand access stream, right? If you're only looking at the last address reference and adding the stride to it. Because you're initiating the prefetch when the load is fetched the next time. This can be too late, because the load is going to soon access the data cache after that. Right? How many cycles are you going to save in this prefetch? Remember, we want to prefetch, I don't know, 10 iterations ahead, 12 iterations ahead sometimes, if the memory latency is really long. So there are solutions to it. There are multiple solutions. One is, you don't just say, you prefetch ahead, basically. You don't just prefetch last address referenced plus the last stride, but you prefetch last address reference plus n times the last stride. Now you're prefetching n instances ahead of this load. And assuming the load will keep its behavior, and if you keep prefetching ahead, you will have prefetched all of those addresses that the load is going to touch in the future. That's one solution. That's last address plus n times the stride. You can generate multiple prefetches, which actually you need to do to get to this point a little bit. But also, people have proposed things like this. Use look-ahead PC to index the prefetcher table, like predict which program counters you're going to access in the future, and use that to index this. This makes sense, especially if you decouple the front end from the processor back end. We discussed this very briefly when we talked about branch prediction. But if you actually have a branch predictor, what you can do is you can decouple the front end from the back end such that the branch predictor is fetching ahead, right? And we know that the back end is actually slow because there are a lot of stalls that are happening in the back end related to the data cache, memory. So if there's a stall in the back end, the branch predictor, maybe this is a better place to do it, but I'm afraid to make your eyes bad. Should really fix this in the break. Okay. So basically, the decoupled front end looks like this, at the simplest way of looking at it. You cannot see it. This is a back end. This is the front end. This is a queue. And this basically supplies the instructions. And front end consists of the fetch engine and the decode engine, and maybe the rename engine, ... Maybe the register file access also. We don't know, depending on the engine over here. This is really annoying, isn't it? Okay. You can make something out of that. How about this? Oh. But basically, you can, the branch predictor is generating addresses ahead, and you're putting a lot of stuff into the queue. So this could be running, I don't know, maybe 1,000 instructions ahead, whereas this is stalling for the long memory latency. Right? That's certainly possible. But now the advantage of this is you're actually generating branch predictions. You may even execute some things over there. I'm not going to get into that right now. But you can actually generate prefetches much, much ahead. If you have this look-ahead PC, which I just showed, you're looking ahead. Now you're actually seeing the access stream while the processor is being stalled in the back for something else. Right? So it can actually generate a lot of prefetches. Okay. Okay. The other way of looking at the stride prefetcher is from the memory's perspective. We were looking at the instructions perspective here. Instructions have strides, but also memory locations or regions may have strides also. So the stride is a property. There's always this question in prefetching: is the stride a property of the instruction, or is it a property of the memory address or memory region you're accessing? And it turns out it's a bit of both. That's why both of these are used. But there are cases where the stride is generated by not necessarily an instruction, but just an access of multiple instructions or multiple things that are going on in the processor. You happen to access block A, and then block A plus n, and then block A plus 2n, A plus 3n, ... And if you actually do keep track of a block address and a stride, you can prefetch things. So stream buffers, which we'll talk about, are a special case of this, where cache block address-based stride prefetching, where n is equal to 1. You're streaming, right? Whenever you see address A, you access address A plus 1. Because you figured out that in this memory region over here, my stride is 1. Then the key question is, how do you track the memory region, right? We'll talk about an existing prefetcher, Pentium 4-like prefetcher, in a little bit. Okay, let's look at stream buffers. This is actually a paper. I don't remember if you read this paper, but this is the paper from Norm Juppy that introduced victim caches. It also introduces stream buffers. So this has a lot of influence in the field. If you're going to write papers like this, I'd recommend. But basically, the idea of stream buffers is simple. In this case, he introduced it in a particular way, but the idea is more generalizable. But basically, you have a bunch of FIFOs over here, and it's called a stream buffer. Each stream buffer holds one stream of sequentially prefetched cache lines. They're kind of looking ahead. And the reason you have multiple FIFOs is you may be operating on multiple streams. If you're adding 10 different arrays, for example, and all arrays are streaming, then you may want to have 10 buffers over here, and you're supplying data to the processor. When you get a load miss from the data cache, you check the head of all the stream buffers for an address match. If it matches, you get the data and put it into the cache. If it doesn't match, then you allocate a new stream buffer, FIFO, and you may need to replace one of them, of course. And this is one particular implementation, but you can see that if your program is always streaming, this works nicely, right? And stream buffer FIFOs are continuously topped off, so when there's a space that becomes available over here, you prefetch from the memory. If the processor has used one entry over here, space becomes available, so you prefetch another one from memory. So you automatically top off the FIFOs. And if you're streaming all the time, this works nicely, right? And of course, when the bus is not busy. And this paper proposes a specific implementation, but the idea is more general. Basically, you can do this in a different way also, which I will describe in a little bit. But this is one example, again, from the paper. You have the next address over here, and you have a FIFO over here. When the CPU needs to access something, you compare the address that the CPU is accessing to the address that's stored, cache block. And if it matches, you supply the data into the cache, and then get rid of it, and then generate the next address, and then prefetch, right? Next address is basically whatever is not in the stream buffer, whatever is next in this stream over here. Right. So it makes sense. Okay, and this is from the paper. Again, I don't need to go into it, but it looks nice. Maybe not nicely drawn, but conceptually nice. So there are clearly trade-offs in stride prefetching, instruction-based stride prefetching versus cache block address-based stride prefetching. So if you look at the stream buffer design, it has nothing to do with instructions, right? It's not observing anything, any program counter over here. It's observing the cache misses that get out of the data cache. Right? And existing processors have things like this, but they're more sophisticated. Okay, so the latter actually can exploit strides that occur due to interaction of multiple instructions. So you may not have a stride in one instruction, but with multiple instructions, you can actually have a stride or stream. And the latter can more easily get further ahead in the processor access stream, actually. But that's not always true. With the decoupled front end that I have over here, you can actually play a lot of tricks. But there's no need for look at PC, clearly, right? This decoupled front end actually complicates things a little bit. Although a lot of the IBM processors actually employ that decoupled front end. Okay, and the latter is more hardware intensive. So if you somehow figure out the strides with your instructions, then it may be easier to do that, especially if someone hints you the stride. It gives you the stride as a hint. But the latter may be a little bit harder. As we will see, we'll actually make it more and more complicated to try to detect strides in a more interesting fashion, like irregular strides. Because programs actually sometimes have the behavior that you don't have a single stride. You do address +2 and then +3, right? Your strides may be not... So if your stride is single, then things are easy. Stream buffers exploit the fact that a lot of the strides are +1, right? You keep going +1. You could also do -1. But what if your striding behavior is +2, +5, +2, +5, +2, +5? What if it's +2, +256, +2, +256? It's regular. It may happen because the data structures are far ahead. So the data structures may be nicely laid out, but you may actually access one data structure and something close by it within the data structure, and then the next data structure is 256 cache blocks apart. Right? So these happen because of how the memory is laid out and how it's accessed in the program. And detecting those more complicated strides become more hardware intensive, clearly. Okay, and also there are more data addresses to monitor than instructions. Okay, so I think this is where I will stop for a while so that we can figure out what's going on with this one. So you can take a break for 8 minutes, and then we'll be... Okay, let's continue. This is where we had left off. Trade-off in stride prefetching. Let's talk about some real prefetchers. So it's not easy to detect strides, actually. And in some cases, there may not be an easily detectable stride, because there may be actually a lot of things going on in the processor. It's not just one load, it's multiple loads that are happening, especially with out-of-order execution, right? And if you have multiple threads, then you have another issue on top of that. So existing processors actually try to do more complicated things because many applications' access patterns are not perfectly strided. Some patterns look random to close-by addresses. You may actually, for example, operate on, even in programs, you may actually operate on a data structure in different ways because of the branches, right? You get to the data structure that's maybe, I don't know, 16 cache blocks big, and you access different fields of it depending on the data values that you have in different fields. Right? So that becomes a little bit hard to predict. You really are operating on this data structure locally, and that's why we're going to talk about locality-based, what I call locality-based prefetchers. There's no easy way of describing this, I think. But how do you capture such accesses is a key question that keeps some people up at night. So I'll describe a prefetcher that's loosely based on Pentium 4 prefetcher. So it's a long time ago, but people have improved it quite a bit. And this is really described in a footnote of the paper, so you should look at the paper. This is one of the papers that I recommend. But basically, a lot of the existing prefetchers keep multiple tracking entries for a range of addresses. And this may be best to actually describe with a picture, but we'll get to it when we get to it. So initially, for regions, let's say, memory regions, initially the tracking entry is not allocated to a stream to keep track of. Initially, all the track entries are invalid, basically. So when a demand miss comes, let's say it's an L2 demand miss, load or store, it doesn't matter. It allocates a tracking entry if it doesn't find any existing tracking entry for the cache block address. Now you start monitoring. And then basically the prefetcher tries to figure out whether there's a pattern. This is probably where I should really jump over here. But it tries to figure out whether the pattern is ascending or descending, right? Based on the next some number of misses that it sees within that region that it's monitoring. If it sees some number of misses or accesses to a descending or ascending region, it sets the direction of the tracking entry, and it transitions into now monitor and request state. And in this state, there's a lot of text, but basically you monitor the accesses to that memory region from a start pointer to an end pointer. You're looking at a region, really. And now the maximum distance determines how far ahead the demand access stream the prefetcher can send requests. That's called Prefetch Distance. If there's a demand L2 cache access to a cache block in the monitored region, the prefetcher requests cache blocks P1 plus, P plus 1, P plus N from the end pointer, assuming you're going up, right? If you're going down, of course, it's clearly p minus 1, p minus 2, ... n. So n is called the prefetch degree, how many prefetches you send. And after sending the prefetch requests, you move the window region. So the idea is very simple, actually, if I describe it this way. Now, how do I switch? Let's see. Let's hope that this works. OK. Let's think that you have this L2 cache. And after the L2 cache, maybe we have these tracking entries. Let's say we have these 4 of those tracking entries. And each of them are supposed to track a region. You can think of the streams, in a sense. So when you get an L2 cache miss to address A, you check whether you're already tracking this in the prefetching tracking entries. Now, if you're not tracking it, you create a tracking entry. What this address A does, let's say this tracking entry now is going to look at address A minus 16, A plus 16. It's going to monitor accesses to any of those. Now, if you see another access, let's say, to A plus 5, you say, oh, my direction is likely positive. Now, if you see another entry, access to A plus 8, now you're more confident. You're doing something in that region. Now, if you see another one maybe to A plus 3, even more confident. You're doing something around that region. Right? And then, after some point, you become confident and you say, oh, I have trained my tracking entry. Now, this trained or confident tracking entry is going to track address A plus A plus 16. Now, now you have a design choice, right? What are you going to really track? Right? So what some designs do is they basically say, oh, I'm going to prefetch a lot of stuff in this region first. So let me prefetch some stuff in this region, and that's a design choice. I don't know. Let's say we've seen A plus 5. I know. Let's say we moved from A plus 5 to A plus 21. Now this becomes my window. There are many design choices here. Okay, so you prefetched a lot of stuff in this window. Now if you start monitoring the accesses to these blocks. Now if you get an access to any place over here, you move the window. Basically, moving the window means, remember, this is the start pointer. This is the end pointer of the trained tracking entry. You get an access to this trained window, which indicates that you're going to do more of this. So if you get an access to here, you say, I'm going to prefetch A plus 22 and A plus 23, and I'm going to move the tracking window from A plus 7 to A plus 23. Make sense? So now you have a moving window. Now if you get another access to A plus, 16 over here, oh, you say, oh, that looks good. So I'm going to prefetch A plus 24 and 25 and move the window. Right? That's the idea. So there are design choices over here. How do you ensure that you don't skip some prefetches? Of course, that happens also. But that's the idea. Ideally, you start with prefetching all of these over here, and maybe a little bit more, and creating a window that you prefetched, and now you start monitoring, oh, has the processor accessed anything that I prefetched in this region? And if you keep getting information from the processor saying, oh, I've accessed stuff, then you start moving the window. And now, as you move the window, hopefully the processor is also moving that direction, so you're always keeping ahead of the processor, even though there is no predictable access stride that you have. Of course, there are design choices. This could be bandwidth intensive if you move things with one access. Maybe you wait for multiple accesses. That's the confidence rate. But this is what I call a locality-based prefetcher. You won't find this information in many places. Yeah.
What if you want to access just one plus more the window size?
Yes.
And we are always reaching out of the window?
Yeah. Then all of these prefetchers have these corner cases where your window doesn't reach, so as a result, you don't capture it. So what happens in that case is, if you actually, for example, if the processor, that's a good point, if the processor over here, your window is this, let's start with the lightest window over here. Your window is this, and the processor accesses A plus 24, Too bad it's out of your tracking window, right? So maybe you have a bigger tracking window to solve that problem. Or you start creating another window, right? So you can have multiple windows. Some of them may be tracking A+7 to A+23. Some of them may be tracking A+24 to A+38, whatever, maximum prefetch distance. And then the problem happens, what if you have overlapping windows? Right. So these are actually real issues, real design issues in hardware. That problem needs to be solved. But it does affect your accuracy and timeliness and everything. But this is one example of a real prefetcher, and it shows you the difficulties of designing the prefetchers, I think. Okay, so the downside of this locality-based prefetcher, as I've just described, it actually can be very bandwidth intensive, right? Because you're really prefetching a lot to keep ahead of the processing access stream. So if your processor stride is A+8, for example, you will capture it, no question about that, because it's a small enough stride to be in your window. So window size is, of course, another design choice over here. But then you may generate 16 requests for just getting one access from the processor. That's a lot of bandwidth, potentially. So how do you actually fix this? Well, people actually add on top of this stride detection mechanisms and feedback mechanisms. And it's also another downside, which is it's limited to prefetching close-by addresses. If you actually have large jumps in addresses accessed, this is clearly not designed to capture that sort of behavior. So you need to have something else to capture it. That's why people actually design multiple prefetchers in existing systems. But it turns out this sort of prefetchers work quite well in real life. So this is actually a paper that was published by the Intel architects in Pentium Proscott. And they showed some good results when they enable or disable the hardware prefetcher. On these workloads, you see significant performance improvements. Like in this case, 97%. But of course, some of these actually are quite predictable. You could capture a lot of it with some other prefetcher also. But I mean, based on my experience also, this is actually a very powerful prefetcher, this sort of locality-based prefetcher, because it can be much more general. It's not reliant on a single stride. But you would really like to augment it with things like stride detection to be more accurate and less bandwidth intensive as a result. Okay, this slide talks about limitations, but it also talks about an upside over here. I'd recommend that you read this sort of papers. I'll complain again that people are not writing this sort of papers from industry as much anymore. It's good to do that. Okay, let's jump into prefetcher performance. As I said, there are many metrics for performance, and we've covered some of them. Accuracy, used prefetches divided by sent prefetches, coverage, what fraction of all of the misses are prefetched, and timeliness, what fraction of the used prefetches are actually on time, with some definition of on time. Time is really a continuous metric, right? It's not a single yes or no. It's not a binary metric. So timeliness can be expressed as what fraction of the time you have covered, as opposed to a binary metric like this. Okay, so these are all important. As I said, it's difficult to achieve good in all of them for some definition of good. Clearly, locality-based prefetchers make the trade-off that they would like to improve coverage at the expense of some accuracy. And you can add stride detection on top of that to increase accuracy. And timeliness is really dependent on your distance. How large is this window that you're selecting, right? So there are other issues. Clearly, bandwidth consumption is an issue. Memory bandwidth consumed with the prefetcher divided by without the prefetcher. If you increase that too much, that may not be good. But if you have idle bus bandwidth, then you can utilize that for prefetching. And everybody wants idle bus bandwidth, of course. But that may be not so easy to get. Cache pollution is another metric. These are extra demand misses that are caused by the prefetcher due to placement of the prefetches into the cache. It's a bit more difficult to quantify because there is a lot of complexity that's going into the cache, but it does affect performance. Okay, let's look at some of these. So prefetcher aggressiveness affects all of the performance metrics. And aggressiveness is dependent on the prefetcher type, as we've discussed. Software prefetchers are different parameter for aggressiveness compared to hardware prefetchers. For most hardware prefetchers, you have these two parameters. Prefetch distance, how far ahead of the demand stream are you remaining? So in this case, for example, in this window-based prefetcher that we looked at, your distance is 16, right? You're assuming that you accessed this. Okay? And as you increase that distance, you become more aggressive. Prefetch degree is how many prefetches do you send out per demand access. So it's a pictorial picture of it, pictorial view of it. Access stream, processor, accesses X. And they have a predicted stream by the prefetcher. And that's your prefetch distance. Ideally, you're far ahead from your processor access stream. So this is a very conservative prefetcher. It's not so much far ahead. This address is maybe a few blocks ahead of the processor. Very conservative. You could be middle of the road. Clearly, you could be very aggressive also. And as you keep getting aggressive, you run into the risk of processor not going into the stream, right? You prefetched a lot, but the processor is going to go somewhere else in the memory access stream. And you prefetched a lot, maybe the processor is going to touch only one of these, and you will still keep prefetching a lot. Okay, so prefetch degree is this basically. Assume your distance is fixed like this. Prefetch degree is whenever you get an access to x+1, how many prefetches do you send out? So in this case, you send out 3. And these are both levers you can use to control the aggressiveness of the prefetcher. And these metrics interact with each other. For example, with a very aggressive prefetcher, with a large prefetch distance and degree, you have different trade-offs that you're making compared to a very conservative prefetcher. So very aggressive prefetcher, as we said, it's well ahead of the load access stream. It hopefully hides memory access latency better, but it's more speculative also. Whereas this one's closer to the memory access stream of the processor. It may not hide memory access latency well, but it reduces the potential for cache pollution and bandwidth contention. So as a result, this aggressive prefetcher is likely higher coverage. It has better timeliness also, but likely has lower accuracy and causes high bandwidth and pollution issues. And this is exactly the opposite. This is likely higher accuracy, not always, again, because you may remember the next line prefetcher. It may not be that good, right? It may have lower bandwidth. It may be less polluting. That's usually true. But it likely has lower coverage, and it's less timely. So we make a trade-off. So this is some data from the paper that I mentioned. So this is basically prefetcher accuracy on the x-axis and the percentage of performance improvement compared to no prefetching. There is some correlation, but it's not perfect correlation, as you can see. Here, prefetcher accuracy is not good, and some application loses performance by 50%. Basically, that's 2x reduction, 2x increase in execution time. That's a lot, right? You double your execution time. But there are also some other applications that don't gain much, even though prefetcher accuracy is very high, right? Because coverage may be really low. Or they may not be timely at all, right? And there are some applications that are over here that gain 300% performance improvement, which is really high. But that actually happens with prefetching because memory latencies are very high. But its accuracy is, if you see, look at this, it's middle of the road, right? 50% accurate. So accuracy is not the only metric. And it's very hard to come up with a model that gives you the performance improvements given all of those metrics because there's so much that goes into it. That's why we resort to simulation in general. Okay, so this is one other example, basically different workloads, single core, instructions per cycle. No prefetching is here. Very aggressive prefetching turns out to be the best thing over here, but not by much compared to the middle of the road prefetching over here. Because it actually helps a lot of programs. If you look over here, keep being aggressive helps a lot of programs because memory latencies are so high, you want to cover it. And some of these workloads are actually have very nice predictable patterns. So mgrid, for example, does multi-grid simulation, and you can imagine it works on these matrices, and it actually is very predictable. But some of the other ones, for example, this one, I think this modeled the atom somehow. I don't remember now. But it definitely had an atom data structure. But basically, this one has very large strides that the prefetcher is not able to capture. So if you make it more aggressive, you're basically going to reduce performance. And as you can see, it loses 48%. This is the one that doubles its execution time as you make the prefetcher more aggressive. Another one, again, reduces performance. Even though it may have very predictable access patterns, this particular prefetcher should not be aggressive in it. So you really need a throttling mechanism. So the idea in throttling, actually many prefetchers and systems are today throttled. This paper is one of the earliest ones in the field. The idea is very simple. You dynamically monitor the prefetcher performance metrics. Which ones you monitor becomes interesting. You throttle the prefetcher aggressiveness up and down based on the past performance. And you change the location prefetches are inserted in the cache based on the past performance. So I'll give you an example. You may decide to classify your accuracy of the prefetcher and also look at the timeliness and look at the pollution you're causing. And if you're very accurate, timely, and not polluting or polluting, then you decrease the aggressiveness of the prefetcher because you're causing some harm over here. If you decrease the aggressiveness, that's good because maybe you're not going to be late still, right? That's one example. But if you're highly accurate and you're late, maybe you increase the aggressiveness to see if you'll get benefit, right? And there are a bunch of other decisions over here, which I'm not going to go into in detail. But basically, you're low accuracy and not polluting and not late, so you may decide to have some action, right? I don't know. So clearly, like with any other threshold-based mechanism, this is prone to thresholding errors. And also, there are a lot of design choices here. How do you determine these choices? So these kind of things are actually good for maybe looking into learning-based algorithms to learn over time. Because there's a lot of data that's input into the prefetcher from many, many workloads over time, right? If you think about a single nanosecond, you're actually getting a lot of requests from different cores. OK, so if you do something like this, well, you can read what that full thing is from the paper. You can actually get the benefits of very aggressive prefetching. So this is the final result, feedback-directed prefetching, it's called. If you look at it, feedback-directed prefetching is the best one compared to the very aggressive prefetching over here. But it curbs basically all of these issues that you see in the workloads, losing performance by 2x. You're not losing performance anymore. You're actually gaining performance by intelligently controlling your prefetcher. And also, but sometimes you're actually losing compared to the very aggressive prefetching, but hopefully not by not much. Although here you're losing a lot, it seems. So you always make this trade-off. And if you want prefetchers, so actually there was a time, and it still is the case, I think, some of these prefetchers, when they're shipping these systems for server workloads, they used to turn off the prefetchers, the data prefetchers, because those workloads didn't have predictable access patterns with the prefetchers that are actually implemented in the processor. So they wanted to do no harm, clearly. But they won't gain also if those server systems are used for, I don't know, workloads like this that benefit from prefetching. So if you have a dynamic mechanism that looks like this, you can curb those downsides. Whenever you design a mechanism, like we've discussed yesterday with run-ahead execution, if you really want it to be implementable, you want to ensure that it doesn't do harm, at least in most cases, right? In this case, we were doing a very big harm to these workloads that may be important. Now we've actually curbed those. OK. So there's another aspect to this, which is energy and bus bandwidth. So you can measure bus bandwidth or memory bandwidth utilized with bus accesses per 1,000 instructions, for example. This includes the effect of L2 demand misses as well as pollution-induced misses and prefetches. So that's what you would like to look at. Number of prefetches sent is not necessarily a good metric, actually. I mean, it's not bad, but you can do better. If you look at how much you change the bandwidth utilization, that's better because it really looks at the overall effect. So it's really a measure of bus bandwidth usage. And this is some data, very conservative, no prefetching, very conservative prefetching, middle of the road, very aggressive prefetching, and feedback-directed prefetching. So if you look at this, the IPC increases clearly. Bandwidth per kilo instruction also increases. And this is the highest over here. So you may not want to actually go from middle of the road to very aggressive because it increases your bus bandwidth by about 30%, even though it doesn't have a commensurate effect on performance. But if you do feedback-directed prefetching, you do better than all of them over here in terms of IPC, and you keep the bus bandwidth in check as well. So your bus bandwidth is similar to middle of the road over here, as you can see. But your performance is much higher. So it's good to keep the bus bandwidth into account. OK, any questions? Otherwise, we're going to move on to more prefetchers. OK, so the throttling is applicable to any prefetcher, clearly. But let's take a look at the more difficult case than prefetching. We talked about regular access patterns, but what happens if you have more irregular access patterns? And there are a lot of applications that have this indirect array accesses, your dereferencing pointers, linked data structures, clearly. Multiple irregular strides, 1, 2, 3, 1, 2, 3, 1, 2, 3, that could be your stride. And people have designed prefetchers that correlate the strides. Random patterns, can you prefetch for them? Generalized prefetcher for all patterns, do you have them? So we're going to talk about these sorts of prefetchers next. Let's start with the correlation-based prefetching. So this is called address correlation-based prefetching. Okay. Basically, consider the following history of cache block addresses over here. Clearly, there's a pattern here, actually. There's correlation. For example, when you access A, if you knew the access stream beforehand, you could guess that you're going to access B with a very high probability next. Right? So after referencing a particular address, some addresses are more likely to be referenced next. And if you see over here, you could create a model, a Markov decision process, or a Markov model over here, after the fact, of course, which marks each addresses as nodes and connects the next nodes, the next accesses, with a probability on the arcs. So after you see A with 60% probability, assuming you have this access pattern, you're going to see B. After you see B with 100% probability, you're going to access C. And after you see C, you have these 3 arcs going out to DEF with different probabilities, right? Now, if you have this information, you can design a prefetcher that can exploit this information, right? Actually, if you have a linked list, A, B, C, D, E, F, you're always going through A, B, C, D, E, F. What you have is really a Markov decision process where the arcs are 100% probability, right? Assuming the linked list is not getting modified, right? Okay. So that's the idea of Markov prefetching using Markov predictors. And you can decide how to implement this. There are many different potential implementations. It's an expensive implementation that I'm going to describe. Basically, you record the likely next addresses after seeing an address A. Let's call them BCD. Next time A is accessed, you prefetch BCD. And depending on what your prefetch degree is and how much you want your prefetch distance to be, maybe you prioritize them based on the probability that you've seen in the past, right? Maybe you've seen B with probability confidence 90%, so you prefetch B only when you see A. So A is said to be correlated with BCD. And this is, you can implement this with a table that looks like this, clearly, right? So if you're going through a linked list, whenever you see A, the next thing you see is B. Whenever you see B, the next thing you see is C. Whenever you see C, the next thing you see is D. So you have entries for each of the nodes, and you have entries for the next node that you're going to access correlated with each of the nodes. And you're looking at maybe multiple. You can actually say next time, you can correlate A with the next 2 nodes, or next 3 nodes, or next 4 nodes. Whenever you access A, you don't just get B, you get B, C, D, E, F, right? If it's a linked list, this works nicely, perhaps. Okay, so basically you can prefetch up to n next addresses to increase coverage. Prefetch accuracy can be improved by also using multiple addresses as key for next addresses. So you can actually get more complicated than this, which we're not going to go into. For example, instead of having A over here, you kind of group them. If you see A and B in some order, maybe together, with very high probability, the next axis is going to be D, for example. I mean, it doesn't happen here, of course, but you could actually record that information. So basically, you correlate groups of addresses with groups of other addresses. Now, how do you index into that structure? Well, you can hash, right, in hardware. You can hash these 2 addresses, index into it, and the next one says, oh, whenever I see this hash, the next one is going to be these addresses, so I'm going to prefetch them. Now, this can improve accuracy because now you have more confidence, another level of confidence. You don't wait to see just one address to prefetch the next 3 addresses, let's say. You wait to see 2 addresses to prefetch the next 3 addresses, let's say. You can wait to see A, B, C, D, E before prefetching the rest of the linked list, right? Yes?
Isn't this something like a trace cache?
Mm-hmm. Yeah, in a sense, I mean, it has similarities, but the trace cache is very particular for instructions. But it does have similarities. It's like an address trace for data. You're right. So in that sense, it's similar. Because the addresses that you keep accessing are repeated. Yes. But we're not storing the data over here. Okay. So now you can quickly see that their design is very, design can become very complicated. Right? How do you actually, so for example, if you have a billion entry linked list, how do you store it over here? Good luck. And that has been the difficulty with Markov prefetchers. They don't work well with very large data structures, right? Because they're really trying to memorize the access pattern in this case. It works well if the data structure actually fits in these tables that you have. Okay. So advantages and disadvantages, I've given you some, but this can cover arbitrary access patterns now, right? Linked data structures, streaming patterns also. If you're doing A plus 1, A plus 2, A plus 3, A plus 4, you can do it. Whenever you access A, you record A plus 1, and you prefetch that, assuming you're repeating again, right? You basically have an array access. You go through the array with a stream of 1. Basically, each entry, I think it's easier to just explain it over here. A picture is worth more than 1,000 words, right? Now you can remember that front end and back end that you didn't see very well before. Okay, so basically, it's basically the correlating address you correlate with, and then this is the next address to prefetch. And you may have a large table for this. If your access pattern is A plus 1, A plus 2, A plus 3, ... A plus n over here, and then you later go over here. The first time you see this access pattern, you have A, and the next address is A plus 1. And then you see add A plus 1, and the next address is A plus 2. ... right? A plus n minus 1, and the next address is A plus n. So you go through this. The next time you go through this access pattern again, when you see A, you prefetch A plus 1. And you can actually index the prefetch address as a correlating address to go ahead. And you assume that you're going to go through A plus 1, and then you prefetch A plus 2. You can again do this, and then you prefetch A plus 3. Right? Of course, it's a terribly inefficient way of prefetching for a streaming access pattern like this. First of all, it requires a streaming access pattern to be repeated. You cannot prefetch before you see the access pattern. And the second of all, you're wasting a lot of space here for something really simple. So it works under some conditions, but it's not the best thing to do, as you can see. Okay. So disadvantages, as we've seen, correlation table actually needs to be very large for high coverage. Recording every misaddress and subsequent misaddress is actually usually infeasible. This works very well for small data structures, but with big data structures, you have a problem with this correlation table. Can have low timeliness. Look at it is limited. Since a prefetch for the next access or miss is initiated right after the previous, that's why we need to do this indexing again. Or we store many, many addresses ahead. Can consume a lot of memory bandwidth if you store many, many addresses ahead, if you want to improve the look ahead, especially when Markov model probabilities are low. And it has actually a very big downside compared to a streaming prefetcher, for example, which is it cannot reduce compulsory misses. Right? It can only record an address it has seen. Right? If it hasn't seen that address, it's not in this table. And streaming patterns are really predictable. You don't need to have seen the addresses, right? If A plus 1, A plus 2, A plus 3, the next logical thing is A plus 4. But this Markov prefetcher is very inflexible for those. So you don't use this for streaming address patterns. So you need to have some other prefetcher to cover them. Okay. Any questions? Thoughts? Let's move to something. Oh, okay, yeah, I was going to say something else. So if you have a linked list that fits into this correlation table, this is not bad. But think about now if you have a very large tree, where each level of the tree it's not a binary tree, but it's an octary tree, let's say. Each level of the tree has 8 pointers to the next level. Now you have a problem with this, right? Because you may always take a different path in the tree. Whatever you stored in the past may not be useful. because it's very path dependent. And your storage may not be very efficient, again. And your bandwidth, if you really want to cover things, you probably want to store all of those pointers in the tree. But then, if you want to be accurate, if you want to cover a lot, you want to prefetch all of those pointers, but then that increases your memory bandwidth. So even though this theoretically may not be bad for some linked data structures, it's really not good for these complicated data structures like trees or priority heaps or things like that. Okay, I'll give you another idea that's a very clever idea, in my opinion. Because it's not as complicated. This is the other end of the spectrum. It's not so complicated. Content-directed prefetching. It's basically a specialized prefetcher for pointer values. People realize the importance and difficulty of these pointer values for a long time. And the idea here is simple. Whenever you fetch a cache block, you identify the pointer values among them and issue a prefetch request for them. You scan the cache block and say, oh, this is a pointer, this is a pointer, this is a pointer. I'm likely going to access them because I'm loading this cache block. So let me issue prefetches for these pointers. And it was proposed in this paper. Now, the upside is you don't need any storage for this. Right? You don't need to memorize or record anything. You're just scanning what you're brought in to the processor. It's beautiful. And it can eliminate compulsory misses, never seen pointers. You're just seeing it for the first time. You're loading this cache block. So it could be much more powerful. Now, the downside is it indiscriminately prefetches all pointers in a cache block. Right? What if you're not going to access them? So you still have the bandwidth problem. And it may not have a lot of look-ahead also, which is not written here. But how do you get look-ahead in terms of this? Now, you prefetch, and then the cache block that's loaded by that prefetch, you could scan the pointers in them also. And then you could issue prefetches based on the prefetch cache blocks. Certainly, you can get look-ahead like that. But you're still limited to a cache block in the end. You're just scanning that cache block. Now, you can combine this with other prefetchers, like next cache block, but you may not be able to cover all of the pointers in the program this way. But it works for some workloads. So how to identify pointer addresses is a question over here. And we've discussed this last time. Actually, the one that I discussed, the Avd Predictor, used a mechanism that's very similar to this. What they did in this work is they compare address size values within a cache block, let's say 32 bits, with the cache block's address. And if the most significant few bits match, then they declare that it's a pointer. I'll give you an example over here. Oh, okay, something happened here. I don't know what that is. Okay, it's over there too. It's not on the screen. Okay, so basically, let's assume that we're accessing this address, and you're loading a cache block. You loaded the cache block. This is the cache block address. And these are the pointer-sized values. Essentially, we want to figure out which one is a pointer. And the mechanism in this paper is to compare the top n bits of the address to the top m bits of all address-sized values. And in this case, you have one match. The top 12 bits over here match the top 12 bits. So you say, oh, this is likely a pointer, so I'm going to issue a prefetch for that address. Now, this may also be a pointer, but you're missing it. Right? So it's not a perfect mechanism, clearly. So if someone tells you what are the pointers, that helps in general. If someone tells you what are likely useful pointers to prefetch, that helps even more. And that's the idea over here. So basically, content-directed prefetching, one of the downsides of content-directed prefetching is it's indiscriminate. So it's actually very bandwidth intensive. So there are cases where it reduces your performance significantly unless you throttle it, you realize it, ... But if you actually provide it with more information from the software, you can actually make this much more effective. So hardware doesn't have enough information on pointers, especially which one. So maybe it can guess. Maybe it can do a good job over there, but it doesn't have information about the data structure layouts, right? And which pointer is more profitable for prefetching, and which pointer you should really avoid prefetching, because some of the pointers may not be used a lot, right? But software does have that information, and if it needs to have more information, it can profile. So the idea over here is to have the compiler profile and analyze the code and provide hints as to which pointer addresses are likely useful to prefetch for. You just mark them with 1 bit or 2 bits, whatever it is. How do you do that is another question. And the hardware uses those hints to prefetch only likely useful pointers. Let's take a look at one example over here. Example from another application, minimum spanning tree computation. But as you can see, it's a link traversal over here. And this is the data structure that we're traversing. You see that there are 3 pointers in this data structure. Pointer to 2 elements of data, and pointer to the next node. Now, this is what it looks like in a cache block. So this is the cache block that contains the data structures and the pointers over here. And when you traverse, you really are bringing 3 pointers for each data structure node. And in a cache block, you may have multiple of these 3 pointers. But when you're traversing, we know that if you're looking for a key over here, so this is how it's laid out basically. In a cache block, this is what you may see. 1, 2, 3 pointers here, 1, 2, 3 pointers. Oh, wait, key is not a pointer. So 1, 2, 3 pointers here, 1, 2, 3 pointers here. So you have 6 pointers. But when we're, and if you're doing content-directed prefetching, it would prefetch for those 6 pointers. May not be a good idea, right? Because we have, as a programmer, you know something about the access pattern over here. Your key is going to either match. If it's matching, you're going to access the data. If it's not matching, you're going to move to the next node. So some pointers are more likely to be accessed than other pointers over here. Clearly, the next pointer is more likely to be accessed. If I were a betting person, I would bet on this key pointer, right? Not the data pointer. Of course, it depends, again, on your data structure, how big it is, ... But if it's a big enough data structure, you're likely going to traverse these next links, and you're not going to touch these D1, D2 much, unless you have a match. So that information can be easily provided, assuming you have the interfaces. And I don't know what this is doing itself, but yeah, assume that somebody provides you that information, saying that the next pointer is more important than the D1, D2 pointers. Then you just prefetch the next pointer, right? And maybe that next pointer too. There's some animation issue over here, which I wasn't able to get correct. Does that make sense? Okay, so if you have these software hints, actually, you can do a lot better. And I think this is a really good direction for systems to be taking going forward. Because with these simple hints, basically what we're trying to do really is convey what the data structure looks like and what we're trying to do at the much higher level to the hardware. A lot of that information today gets lost in between, right? We don't have the interfaces to communicate it. Very little things get communicated, like prefetch instructions. But the hardware has almost no information about what data structures it's examining today. So if you actually fix that interface, there could be big gains that can happen. And this is one attempt at helping that interface in a specialized way. Okay, so clearly there's no single prefetcher that can cover all patterns. So people have designed hybrid hardware prefetchers, and you can be sure that whatever you're working on has those, is prefetching right now with different hardware prefetchers. So streaming, striding, linked data structures, localized random with the locality-based prefetchers, for example. So use multiple prefetchers to cover all patterns. You get better prefetch coverage. And like with anything heterogeneous, you get more complexity, more bandwidth contention, and prefetchers start getting in each other's way, potentially. So you need to manage accesses from each prefetcher as well. Okay, this is obvious. Let's move to a different class of prefetchers, which is execution-based prefetchers. So people always try to improve the coverage of prefetchers. And execution-based prefetchers are very good at executing the program, or a portion of it, or a thread, to do prefetching for the main program that you want to accelerate. Basically, the idea is simple. You pre-execute a piece of the pruned program solely for prefetching data. Of course, if you want to be really efficient, you want to only distill pieces that lead to cache misses. How do you do that is a question. So I'll define some terminology. Speculative thread is a pre-executed program piece that does this prefetching, and that can be considered a thread. It's really a thread in the end. Like we've discussed yesterday, when you go into run-ahead mode, you really are switching to a different thread. That's purely speculative, right? Of course, that thread is not completely invisible to any software outside, because we're not reporting any results from it. But you could do this very explicitly. It could be a software visible thread also. In fact, the operating system can do this, right? It can launch a thread to do prefetching, and it does actually. It looks at the access patterns that are happening to the I/O subsystem, and it launches a thread that prefetches blocks from the I/O subsystem. Actually, you could do run-ahead execution at the operating system level also. If you get a page fault, you keep executing the program. It turns out that idea was proposed. In the past, it's called speculative I/O hint generation, as early as 1999, I think. And that's what they did, essentially. When you get a page fault, you keep executing the program. Of course, you ignore the stuff that doesn't exist. And you generate other page faults that you're likely going to you will likely see in the future. That got the best paper award at OSDI in 1999, I think. I'm not sure if it's employed in existing systems. I don't think it is. Okay, but basically, that speculative thread can be executed on many different places. So now your trade-offs are even bigger. On a separate processor or core, on a separate hardware thread context, fine-grained multithreading. Some of those threads in the fine-grained multithread machine could be doing prefetching. Or on the same thread context in idle cycles during cache misses. Run-ahead execution is one example. But instead of doing run-ahead execution, you could switch in some other thread. When you're stalled for a cache miss, just switch in some other thread that's specialized for prefetching, right? Okay, so there are many issues. How do you construct the speculative thread? You could do it at the software level, prune the program somehow, and insert spawn instructions or fork. You could do it at the hardware level, and again, prune and spawn instruct, or use the original program without any construction, which is what run-ahead execution does, again. But execute it faster without stalling and without having correctness constraints. The key is this thread needs to discover misses before the main program gets to them. As a result, it needs to avoid stalling or waiting, or it needs to compute less somehow, right? If it does exactly the same thing the program is doing, you're back to square one. So you need to avoid stalls, and you need to compute less, at least one of them. So to get ahead, in addition to this, basically, you can, to enable this, basically, you can perform only address generation computation, maybe important branches that lead to prefetch requests, useful prefetch requests, or you can do value prediction, right? The threads you want to execute, some of the values may be predictable in the program, and you supply them, you just predict them, as opposed to generating all those values by executing the program. You want to minimize the computation, right? And it's purely speculative again. So there's no need for recovery of the main program if the speculative thread is incorrect. The sole purpose is prefetching data. Now, if you do it at the software level, your thread will, again, for example, if it gets a page fault, you need to handle it. Right? You need to decide, am I going to handle this page fault or not, right? If it's a purely speculative thread, you probably shouldn't. But it may help prefetching again, right? So you have a design choice over there. Okay, this is a beautiful picture that I borrowed from the Zilsa Sohi paper that basically shows that the idea is even more general. But let's take a look at this load instruction over here first. So we want this load instruction to be a cache hit. So long before the load, we fork a speculative thread that does some computation that leads to the load over here, and then executes the load over here speculatively, gets a cache miss. And when the load and the cache miss gets serviced, and this runs in parallel with the main program over here. This is the main program. When this load gets to the when this main program gets to the load, it gets a cache hit because the speculative thread executed in parallel with this main program, and it already prefetched the data. That's the beauty of it. As a result, you get speed up. But the idea is even more generally applicable. We've talked about this actually briefly when we talked about branch prediction. You could do the same thing for branches that are hard to predict. You could fork a thread that basically executes part of the program, computes the branch condition, maybe not perfectly again, and feeds it to the front end before the branch is executed. And when the branch is executed, you need to somehow synchronize that this thread executed for this branch and use that prediction as opposed to the branch predictor. That's the idea. So you could do it for any problem instruction, actually. In fact, some people called it problem instructions or delinquent loads, delinquent instructions, but it's not in these papers. Okay, so clearly there are many issues over here. Some of the issues, where to execute the pre-computation thread. I'll call it the pre-computation thread now, but it's the same thing as pre-execution. So you could do that as separate, and there are trade-offs which I don't think we can go into, given the amount of time and given that we're going to talk about the exam also. You should think about the trade-offs. Separate core, least contention with the main thread, but then maybe the least benefit also. You're not prefetching into the caches. Separate thread context on the same core, more contention, but maybe the most benefit, or a good amount of benefit. Same core, same context when the main thread is stalled. Maybe less contention, but maybe not as much benefit because you're not doing it in parallel with the main thread now. When to spawn this? Where do you insert the spawn instructions? How far ahead do you go? Same thing happens here. If you do it too early, prefetch may not be needed. If you do it too late, prefetch might not be timely. Right? When the main thread is stalled, you can do this again. That's another design choice. When do you terminate the pre-computation thread? If you're doing it in software, you can actually insert cancel instructions, right? If you figured out that this thread is not going to be useful, under some conditions, you can cancel the thread. Or, again, based on throttling, you can throttle the thread. So there's a huge design space over here. I'll talk about some paper that produced results on real processors. This is Intel's SMT hyperthreading processors. But basically, this paper looked at difficult to prefetch data structures and talks about all of these questions, which I'm not going to go into. But this is a nice picture that shows how you can do it or when you can do it. This is the main execution, and this is the pre-execution. While the program is going through this pointer chain, hash table access, let's say, you're doing many, many accesses to the same hash table. When you're doing one of the hash table accesses, pre-execution thread is doing an independent hash table access. And maybe you have 3 pre-execution threads that are doing the independent hash table accesses, right? So when the program gets to here, hopefully all of that data will be prefetched into the cache. And similar thing happens with array accesses that look like this, and you can actually prefetch these sparse arrays before you finish this array, and this array before you finish that array also. You could do it across function calls. When the program is operating on this function, maybe you're prefetching for a later function, ... right? You could do it also on different program paths. When your program is operating over here, maybe you have a speculative thread that is prefetching for this then part, and maybe you have another thread that's prefetching for the if part, right? So there are many, many cases, and this paper discusses a lot of them, and I just copied and pasted one part of it. This is, again, MCF. MCF is a problematic workload. It does vehicle scheduling, as we've discussed. As you can see, it's looping over trips lists. But basically, it's going over multiple lists over here. So if you look at over here, for a number of trips, for each trip, it's doing something, and then it has this loop to schedule the vehicles, I assume. But basically, while you're working on this loop, you can, before you start working on this loop, you can start a pre-execution thread that works on the next loop, next trip, basically, over here. That way, you parallelize across these loops. And you can see they have a pre-execute start instruction that starts the pre-execution from here. Oh, it's not working anymore. From here. And the pre-execution thread basically gets the context here, and then it increments this, and then it checks whether the loop should exit. If the bigger loop, the for loop, should exit, then you have a pre-execute stop instruction. As you can see, you're out of the loop, so you don't need to prefetch. Otherwise, it goes back and starts to execute speculatively everything that you see over here. So it goes into this part, and then it goes into here, and then it has a pre-execute stop over here. So it prefetches only one iteration ahead in this case. And you can read this for more detail. But basically, somebody transforms the code to add these instructions. It could be the compiler, it could be the programmer, again. And these are the instructions that are added. You start the pre-execution, and you obtain a thread ID. And, of course, there are some conditions over here which you can read. So basically, they stop automatically when max instructions have been executed, for example, in the pre-execution, so that you're not actually spending all your time and resource on pre-execution. And you can also explicitly stop the thread. And also, you can cancel, terminate somebody else can cancel the thread, right? That's why you have the handle for the thread ID. Okay, clearly this is in C syntax, but it's better that it's in C syntax and not ISA format. So what's the benefit of this? This paper actually shows pretty good results. If you look over here, you get, on this workload, you get 36% performance gain. On many workloads, you actually gain performance. Of course, this is all hand-coded. In some workload that you lose performance. That doesn't look good, but it's not terrible. Okay, and if you're interested in this, I'd encourage you to read this paper. So you could do this. This is a purely software approach, actually. There's no hardware other than this ISA instructions that are involved. You could do it purely in hardware also. The hardware can construct this thread as well, but that may be hard. So I'll talk about the problem instructions a little bit also. Basically, you have these problem instructions that you can prefetch for. And the thread you construct for these problem instructions that can actually be very simple. That's the whole point of this example that I'm going to go through. You don't need to understand everything. But it turns out for this program, this tends to be a cache miss much of the time. And this branch tends to be not so well predictable. So you have two problem instructions that are close to each other. So what do you do? So first of all, where do you insert the place to fork the thread, fork the pre-execution thread? You may actually want to insert it outside that call over here. So this is the add to heap call that we were looking at over here. This is not good. Basically, you add to heap, but this is called from somewhere else. And maybe you actually elevate this fork point to outside that call, right? Now, this is actually hard to decide where do you put it. Again, with all of the other issues that we've seen with software prefetching, this fork point insertion tends to be not so easy to determine. Because again, there's a lot of stuff that goes into this, right? Which we're not going to go talk about. You may actually start a thread over here, and the program may branch out somewhere else, so that thread is completely useless now, right? Okay, but the main point that I would like to emphasize over here is you have this assembly for the add to heap function, but if you want to just construct a thread that leads to prefetching for that load and pre-computation for that branch, those problem instructions, that thread is much smaller than the original code, as you can see over here. And the authors write the slice contains a loop that mimics the loop in the original code. Right? It doesn't do exactly the same things, but it mimics that loop. So it's different instructions, and it can prune it significantly. So you don't have to have all of this code over here. Okay. We're not going to go through this code. You can do it on your own, though. And those are very good papers that talk about these things. So run-it execution, we've covered this already. Clearly, it's a method for doing this sort of pre-execution. Right. Okay. Okay, I think I've said a lot of this. So there are advantages and disadvantages of run-ahead versus other execution-based prefetchers. You should probably be familiar with these. Clearly, run-ahead is very simple. You don't need to construct the thread. You don't need to go through all of this effort of constructing the thread. So people have proposed mechanisms to construct this thread in hardware, which turns out to be very hardware intensive. You could do it in software. You could do it at the programmer level. But it's a lot of effort, regardless of wherever you do it. The nice thing about run-ahead is it gets rid of that effort. Of course, it comes, maybe it's not going to be as beneficial also, right? It's simple, but it cannot cover an arbitrary pattern, perhaps. It's limited to whenever you get these cache misses. Right? So if you can actually extend the run-ahead to be more powerful, maybe you can get closer to the execution-based prefetchers also. The downside of execution-based prefetchers is you need a context to execute them, and you need to go through all of that effort. Okay, so one question is, can you make run-ahead even better by pruning the program portion, execute in run-ahead mode? That remains to be seen. Okay, I had this slide before also. Basically, it's not just the run-ahead mode, but this thread construction is purely speculative, right? The goal is to find and generate cache misses that would otherwise stall execution later on. Then the question is, how do we achieve this goal most efficiently and with the highest benefit? So you really need, when you construct these threads, find and execute only those instructions that lead to cache misses, if you're doing it for prefetching. How is always a question. Okay, let me cover the pros and cons of execution-based prefetchers, and then we'll take a short break. So basically, you can pretty much prefetch for any access pattern in this case, because you're really executing code to do prefetching. And depending on how you do it, it can be very low cost, but it can also be very high cost as well. but Runahead is one of the lowest cost examples of this. Okay, we already said this yesterday. It can be bandwidth efficient, Runahead execution. It can be bandwidth efficient even if it's a thread-based thing, right? You can be very careful in what you actually execute in that thread, right? You're not really trying to memorize some addresses. So the locality-based prefetcher, for example, that we've discussed, it's very bandwidth inefficient if you're really not careful, and it's very hard to be careful while getting high coverage. Whereas in this case, you're really specializing a thread to do the prefetching for you. So the downside always is you depend on the branch prediction and possibly value prediction accuracy, other than the complexity of it. So some approaches may be very complex. But now you depend on the branch prediction and possibly value prediction accuracy. Mispredicted branches dependent on missing data throw the thread off the correct execution path, similar to Runahead execution again. So some people eliminate those branches, but then once you eliminate those branches, you may actually reduce your accuracy in prefetching. So it's a trade-off, basically. Your branch prediction and value availability affects how well you can prefetch in that speculative thread. It can be wasteful in a different way than bandwidth waste. You're really wasting instructions, just like we saw in Runahead, right? You're speculatively executing many instructions, so controlling this is a really good idea. As we did with Runahead yesterday, right? We tried to get rid of these instructions that are not providing us benefit, these Runahead mode instances. Whereas in this case, with the threads, you can do something similar, right? You need to throttle the threads. So if you figure out quickly that these threads are not providing us benefits, then maybe not even launch them, even though there's a fork point in the program. So you can do things like that. And, of course, this can occupy a separate thread context depending on how you do it. And usually, it occupies a separate thread context. Remember, I talked about even Runahead execution can happen on a different thread context. That's how IBM Power 6 implemented it, right? Because they said, oh, this single thread performance is important, and we're going to go into Runahead mode when we get a cache miss, so I'm going to use the thread context that is next to me in my multi-threaded processor. That may not be a bad idea, but you're now occupying a thread context. Okay, and you have complexity in deciding when and what to pre-execute, right? That's true for Runahead execution, but less so because you're stalling the processor. Whereas here, in the more general case, when do you actually execute this thread? What do you pre-execute? There's a huge design space. But if you do it well, this works well at the software level also. Okay, this is probably a good place to take a burning question and take a break. Any burning questions? Does it sound exciting? Cool. Now we can take a break for, how about 7 minutes? We'll need to spend some time for the exam discussion. Okay, let's continue so that we have some time for discussion at the end. Now that we've covered the broad space of prefetching, let's look into more efficient prefetching in multi-core. Basically, prefetching in multi-core has similar issues like caching in multi-core. You have shared data. How do you prefetch for coherence misses? We've covered some of this earlier, right? Prefetching private data versus shared data. We've discussed that. There are a lot of issues over here, actually, prefetching. People are trying to prefetch shared data by predicting which processor is going to access the shared data. But that turns out to be not so easy to do always. That's why, as I said, a good way of designing systems may be keeping the shared data in one place and shipping the private data to that place, as well as the functions that operate on shared data. But you remember that in the heterogeneous multi-core discussion. But people still try to prefetch shared data somehow. Not so easy. Prefetch efficiency becomes a lot more important, clearly, in multi-core. Bus bandwidth is more precious. Cache space is more valuable. We've seen this in caching as well. And you put another source of interference. One core's prefetches can interfere with other core's requests. One core's prefetches can also interfere with that core's demand requests in the memory system, right? You get more conflicts in the cache, more contention in the bus, DRAM bank, row buffer. And if you're not doing prefetching carefully, then you're actually wreaking a lot of havoc in the entire system, right? For both your own demand requests as well as somebody else's, some other programs' requests, prefetch or demand. In fact, I will show you in a little bit that even if you're doing accurate prefetching, you're interfering with someone else if you're aggressive, right? So that could degrade performance. So there are two key issues over here. One is how to prioritize prefetches versus demands of different cores or the same core. And how do you control the aggressiveness of multiple prefetchers to achieve high overall performance? Apart from the design of the prefetcher, your design of the prefetcher should be careful to begin with, but we've already discussed some of those issues. So in multi-core, there's this interesting thing that you need to coordinate the actions of independent prefetchers also somehow if you want to get the best system performance. If the prefetchers are doing some things, like if you're doing feedback-directed prefetching on different cores and you're not getting feedback from other cores, then you have a problem. Because you may actually be increasing your aggressiveness thinking that you're very accurate, very nicely timely, the prefetcher is doing well, but you may be destroying the performance of some other core that's doing whatever, right? It could be prefetching or not prefetching, but because your prefetcher is controlled based on local information, you may actually lose performance significantly. So you basically need more global information. Okay, so we're going to look at some ideas, not all of them, and there are more ideas to be developed over here, I think. And controlling prefetcher aggressiveness is one of them. And this coordinated control is interesting because the feedback-directed prefetching that I discussed earlier, as I said, doesn't work. So I'm going to give you some ideas on this coordinated control very quickly. In fact, if you're thinking about different ways, these cores are independent agents. They're sharing some resources. Maybe there are different ways of thinking about how to manage them, right? Maybe you actually manage them with game theoretic approaches so that you give incentives to the cores such that they have the right incentives to do things nicely, right? But we're not going to even go there yet. But there are, I think, very interesting potential possibilities here with different fields interacting. Okay, so basically, aggressive prefetching improves memory latency tolerance when many applications when they run alone. But if you have concurrently executing applications, you can get system performance degradation and bandwidth waste. And one of the problems is prefetcher cause intercore interference. Right? This is something we did not tackle so far. Prefetches of one application contend with prefetches and demands of other applications. So this is some data related from this paper. Motivation. So let's say you designed a prefetcher. You look at what potential you're leaving on the table. And that's one of the things that we looked at. And this is the performance improvement that you would get if you ideally removed this interference that you cause to other cores. And you can read the paper for more detail. But basically, that interference leads to a lot of performance degradation or performance that's left on the table. So let's take a look at why even accurate prefetchers cause this interference. So let's say we have this demand request from core X to address Y. We're going to look at some examples of what happens between different cores. This is what you have in the cache. Again, this is core 2's demands. Core 0's prefetch, core 0's demand brought these different addresses. And this is what's happening in the memory controller, and these are the requests that are being serviced, these prefetch requests. Now you can clearly see that this prefetch request is delaying this demand request. And this prefetch request is from core 3, right? Okay, I'm going to go through this relatively quickly because it's kind of obvious. And these prefetch requests kick out these demand requests from core 2. And these prefetch requests may be from different cores, as you can see over here. And now core 2 demands the address that's kicked out, right? So you have a problem. So you get a miss. And core 2 demands that address, ... and that gets serviced. Now some other core requires some prefetch. And because it's a row buffer hit, these prefetches may become ordered earlier. So your policies, if they're not prefetch aware, can delay things significantly, as you can see, right? And there are many, many other animations that you can make related to this. So you do need to take into account request type in your decisions across the hierarchy, basically. Okay. So if you do local prefetch throttling, that may not be good. Let's take a look at this case. You have these two cores somehow occupying the cache. And you have these prefetchers from these cores. Let's assume that core 0 and core 1 are prefetching, and they're kicking out data from these cores. And what might be happening is they have used prefetches. As a result, they're going to throttle their prefetchers up. As a result, they will keep prefetching. Now, if they keep prefetching, they're going to keep displacing more things from the cache, and this core will start demanding again. So you actually run into situations where you increase the accuracy of your, you throttle up your prefetcher because you think it's accurate, but it's kicking out a lot of stuff that this core really needs, right? So you're actually increasing the requests that you make to the memory system overall. So that cannot be good, clearly. One way, of course, of solving this is partitioning the cache, right? Such that the prefetches of one core don't affect another core. There may be other ways. So one other way is controlling the workload, but I'm not going to go. I'm going to skip this. You can look at the slides if you're interested. But basically, what this is trying to show is if you do local-only control, you actually can lose performance. Local-only control that's not aware of the interference that's happening between the cores, however good it may be as a local decision, it's not good enough. It loses performance. You don't want to. In fact, you don't even want to control your prefetcher if the control that you're adding is going to lose performance, right? Okay. So basically, how do you actually coordinate different prefetchers' actions? There are many ideas over here. I talked about game theoretic approaches, which are actually very interesting also. But there usually things that have been thought of could be utility-based, prioritize prefetchers that somehow provide the best marginal utility on system performance. You do cost-benefit analysis. How do you do that? That could be interesting, which we're not going to go into. I'm going to give you a glimpse of the heuristic-based approaches. Basically, a simple way could be having a global controller that overrides the decision of the local controllers, having more hierarchical control, basically. Of course, if you want to do that, you need more information. So this is one example. You have different cores. They each have a local controller, and they make a throttling decision. We're going to get rid of that throttling decision over here. Now we're going to have some global control over here. Local control's goal will be to maximize the prefetching performance of core I independently, assuming there's nothing else happening over here. Now, global control's job would be to keep track of this prefetcher-caused interference in the shared memory system and control it somehow. Well, how do you control it? By basically communicating with the local controllers over here. So you get input accuracy from the memory control. You get some bandwidth feedback. You get some cache pollution feedback. And how do you do it depends on like what your system looks like, of course. But global control either accepts or overrides the decisions made by local control to improve overall system performance. Right? So a local throttling decision gets either overridden or accepted. You can make a final throttling decision. So what do you need to take into account over here? Clearly, these prefetchers' local metrics, accuracy may not be the only one. But clearly, you need to take into account pollution, like which prefetcher is causing pollution to others. You probably don't want to throttle up a prefetcher that's destroying the performance of other workloads in the cache. And also, how much bandwidth you're consuming over here, and how much bandwidth do others need. So you can actually keep track of which cores need how much bandwidth and try to distribute them accordingly. So one example, you may actually have high accuracy over here, and the local controller says, I'm going to throttle up. Global controller says, you're polluting too much, and you're consuming high bandwidth, and others need a lot of bandwidth, so don't throttle up. Of course, it makes sense. So it's basically control. It's a control system. And this can be designed in many ways. Heuristic-based approach is one way. You could really design a control theoretic approach. You need to then feed the inputs accordingly. It could be a machine learning-based controller, ... which we're not really going to get into. This is a heuristic-based approach, right? Heuristic-based always has issues also, but every other design also has issues. Okay, so one example of this is figuring out what cases lead to severe interference and enforce the throttling down of the local decisions in the case of severe interference. For example, if you're causing high pollution and if you're inaccurate, maybe that could be classified as severe interference. If you're causing pollution, if you're highly accurate, if you're consuming a lot of bandwidth and others need high bandwidth, again, that may be severe interference, even though you're maybe very, very accurate. Right? Okay, and this improves performance. It actually, so if you look at feedback-directed prefetching, local control only, it loses performance in a number of workloads when you apply it to some system with shared caches and shared memory controllers. But once you add this global control back, you buy back a significant amount of performance and actually improve performance. Okay, Any questions? Sounds interesting. Of course, reasonable, hopefully. So there are a lot of other issues. How do you design the controller to be prefetch aware, which I'm not going to go into a lot, I think. Although these slides are Changju slides that are, as you can see, right? I never recommend these, this color. Do you guys like this better? Let's take a vote here. Blue is good? No? Okay, good. Then he also realized that, and he changed the slides to be white later. But yeah, this is blue. Intel uses these slides, actually. Intel slides are blue. Okay. But basically, one of the questions is, how do you schedule prefetches versus demands? And these are static policies. Demand first always prioritizes demands over prefetch request. Or you can make them equal. Prefetch first doesn't usually make sense. There are cases where it may make sense, but usually doesn't make sense. But neither of these actually perform the best because they don't take into account usefulness of the prefetches, how well you're doing, and they don't take into account the non-uniform access latency of DRAM as well. So you can run this on your own, I think. I'm just going to show you some results. If you do demand first over here, you prioritize the demands. As a result, you get a lot of row buffer conflicts. If you do demand prefetch equal, because the prefetches are hitting in the row buffer, assuming you're streaming, let's say, in this case, you actually get better performance because your accesses lines up in such a way that keeping demands and prefetches equal brings the data earlier before your accesses. Right? So you save a lot of cycles. So sometimes keeping demands and prefetches equal in the memory system may be a good idea in a single core case. And sometimes it's the other way, actually. It turns out demand first here is better because it prioritizes the demand that's really needed, but the prefetches are not needed, right? Or they're needed much later, right? They're useless for now. So if you can somehow recognize that, you can come up with a much more intelligent policy. Let me go over here. Basically, it's very workload dependent. Some cases, demand prefetch equal is much better, as you can see over here. It's a lot better. In some cases, demand first is much better. So you really would like to get the best of both worlds. The question is, how do you do that? Well, if you take into account prefetch usefulness, you can actually try to guide that policy. That's the one idea. And the second thing that we haven't really discussed, what happened here? Okay, yeah, second thing we haven't really discussed is this. You really want to eliminate useless prefetches somehow. And if the prefetch is waiting for a long time in the memory controller and no one has requested it, that may be one indication of the prefetches being useless. Of course, you have trade-offs over here in the timeline. So dropping those prefetches early may be a good idea. People actually propose other things like pollution filters. If you can somehow, if you can somehow predict that your prefetches are going to be useless, you can prevent them also. And then you can feedback that information to your prefetcher. Okay, so ideally you don't want any useless prefetches because they actually cause a lot of problems as we've discussed. Okay, I'm not going to go into more detail. There's a lot more to be said about prefetching and there's a lot more stuff to be done because it's such an important thing. Actually, if you go into a design team of a high-performance processor today, probably you're going to be working on prefetching because that's where big gains are to be made in terms of performance. Because if you actually come up with a good prefetching algorithm, you can overcome this huge bottleneck, which is the latency bottleneck. Right? So you will need to touch prefetching somehow. Well, I don't know if I want to go over this. Let's see, how much time do we have? We have some time. Let me give you the basic idea of this also. So with prefetching, you need to re-examine some policies. This is really, actually, this is something surprising that Vivek found out. I like talking about this because you really need to think the cache replacement policies that you have done. It's really surprising, actually, that no one has done this before. So I'm going to give you the idea. Basically, the idea of original thinking, if you will. Existing caching policies can result in significant cache pollution, especially for prefetch blocks. So let's say existing policies, you get a cache miss, your insertion policy to the MRU position, right? You get a cache hit, your promotion policy says you promote that thing to the MRU position. Right? So we're going to look at this promotion policy. Now, are these good policies for prefetch blocks? basically, let's classify prefetch blocks into 3 categories: blocks that are unused, blocks that are used exactly once before evicted from the cache, blocks that are used more than once before evicted from the cache. And if you actually do a study, simulation study, that characterizes the blocks, lots of the prefetch blocks are actually unused. So this is similar to lots of the fetch blocks are also unused, right? But it's very interesting. Your prefetcher is actually maybe very aggressive in some of these cases. And most of them are used once if they're used, right? So this fraction of the prefetch blocks, in this case, almost 100% of them are used once. And there is a very small fraction of them, if they're used more than once. Right? So basically, 95% of the useful prefetch blocks are used only once. And this, there's an explanation to this. Typically, large data structures benefit repeatedly from prefetching. And blocks of such data structures are unlikely to be used more than once, because you may be streaming through them, right? Again. So, and also many applications clearly have a significant fraction of inaccurate prefetches. So you want to eliminate them somehow by inserting them in the right position. You don't want to insert them in the MRU position. But as we've discussed in caching, you probably don't want to insert anything into the MRU position to begin with, right? You remember the dynamic insertion policy? You really want to be careful about what you insert where to ensure that you're not polluting the cache and you're not thrashing the cache. So let's look at the traditional promotion policy within the context of prefetches right now. You get a cache hit to a prefetch. The natural thing to do is to promote to MRU. But this is exactly what you don't want to do, right? Because the data that I've shown you earlier says you're not going to use it again. It makes no sense to do this, actually. So, and the problem exists with all of the policies, dynamic insertion policy that we've discussed. They all promote whenever you get a hit to a block. But if you have this data that I've shown you, the right thing to do perhaps is this, right? Whenever you hit a prefetch block, you say, oh, I'm going to be done with it because it's likely that I'm going to not reuse it. And it turns out this actually improves performance significantly. And it's a very, very simple thing to change in the cache. And the other question that we've discussed very briefly early on, where do you insert a prefetch? This should really be guided by how good the prefetcher is doing at that point in time. You don't want to insert inaccurate prefetches into the MRU position. You really want to do this adaptively. Okay. Okay, and there is more work. Prefetching in GPUs is also very interesting, but we're not going to talk about that. And how to do that efficiently, because GPUs are very, very bandwidth constrained, right? If you don't do that carefully, you can easily destroy the performance, because you're taking away bandwidth from something useful. So how do you do it? So doing it actually requires a lot of care. You need to coordinate that with scheduling policies that you have in GPUs. And there's a really interesting interaction between prefetching and scheduling, and many, many other things also, but I think it's a good idea to stop here. Any questions? Any burning questions? Okay, no burning questions. Yes, there's a burning question.
For the demanded cache data, I mean, what is the proportion that the data is used only once and then being
Yeah, that's a very good question. There have been studies that looked at that. It's not as low as the prefetches. But I see where you're going, basically. If you can actually guess that, that's essentially what a lot of the reuse predictors try to do, whether you're going to reuse it or not. If you can guess that, you can come up with similar policies. But the fraction is much higher, actually. Yeah. Okay, any other questions? Thoughts? We've covered a lot of material, actually. The prefetching, people spend a lot of time to optimize. Right? Hopefully this gives you the full picture. Okay, maybe that's a good time to talk about the exam. You guys want an exam right now? Probably not. Okay, so here's a proposal. The proposal is to basically make life not hard for you guys. And I want you guys to learn, basically. That's the most important objective of this course. Learning and growing, that's it. So the proposal is you have a deadline for the lab Monday. We push it back to Friday, next Friday. That gives you more time on the lab deadline. And then we push the exam back 1 week into the future. That's December 7th. Basically, not Thursday of next week, but the Thursday of the other week. That enables you to streamline the labs, and we're going to have only one more lab after that. There's no time to do 2. And we're going to start that after the exam, and you'll have 2 full weeks. We can start earlier, of course, if you want. The lab will be out earlier. And this gives you a full week to actually study for the exam if you're going to study. I assume some of you may want to study. What do you think? Does that sound good to everyone? Anybody wants to object to it? No? No objections? You can object. Sounds good? Okay, let's do that. That's one item of business then. Then the exam is set to be December 7th. It's not exactly a midterm, but it's we're not going to cover a lot of these things. I think it's better if you actually digest some of the material. As I said, we're not going to cover anything this week. And if we update that, we're not going to update it forward in the sense that we're not going to cover new material. But if we actually decide to cover even less material, we'll let you know soon. And that may happen, actually. I just had too many deadlines to think about it. Okay, so that's one thing. And again, as I said, I want you guys to learn. This is an elective course, so you're here for learning. I know that, and that's the goal in the end. So exam, a little bit of the logistics of the exam. Basically, it's going to be similar to the homework questions, but not the key will be testing your understanding of the concepts. Right? That's what I'm really after. Do you understand how a memory scheduler works? Can you reason about it? Can you reason about the trade-offs, just like we've done in the class, right? Can you solve some questions related to caches, like basic questions, right? If I give you, for example, a complicated question, can you parse it and make it easier? Like I like some of the cache questions, reverse engineering questions. So you might want to study those things for sure. Or the GPU questions that we had, for example, where we have code examples and you figure out what should be true about the arrays to get this sort of utilization, right? So those questions are actually testing your understanding of the concept. And if you understand the concept, you can solve the question. So that nothing is really memorization over there. So I don't like testing for memorization in general, unless it's a really fundamental concept. For example, if I ask you, what are the 3 key bottlenecks in the parallel portion? Hopefully you guys will be able to tell me. Or what's Amdahl's law about? Oh, that should be easy, hopefully. But synchronization, resource contention, and load imbalance, right? Those are 3 key bottlenecks in the parallel portion. So I may ask you that one. But that won't be a really huge question that actually gets you, I don't know, 100% of the grade. Clearly not, right? So exam will really be about the understanding of the material. So in that sense, memorization is really not what I'm after. So look at those questions where we did a lot of reverse engineering. Those are interesting, I think, because reverse engineering almost always tests your understanding. And I don't want to make it extra tricky, but the questions that we have over there are actually, I think, good enough in the sense that they will give you an example. And we may actually put more questions, I'm not sure. Or we may actually point you to, oh, these questions from the homework may actually look like good exam questions. Yeah. But some of the, like, I don't want you guys to, you don't really need to know exactly the details of how a locality-based prefetcher works, right? You need to know the concept. Well, you don't need to know anything about prefetchers for this exam, but I'm giving examples over here. So I'm not going to ask you, for example, how dynamic insertion policy works. Explain to me. I'm not really interested in that. I'm really interested in whether you understand the concept itself. I'm not going to ask you how parallelism or batch scheduling works. No. I may describe you how parallelism or batch scheduling works and ask you some other question building on it, right? What would be the batch size given that I describe you this policy, right? Then you need to understand how things work in general and use that description. So in a sense, there's really nothing you need to memorize. You just need to understand the concepts and the trade-offs. Now that said, I think it may help you guys to bring some notes if you would like to. Would that help? Yes? No? Depends on the question. Well, I think so. For example, I found this in the past. Whenever I took exams, I used to write notes, and I never looked at them in the exam. If the exam is testing what I said, basically, then I basically don't look at them. Maybe I look at them once with, I shouldn't look at them with the question that I gave you an example of, with the, what is the bottlenecks in the parallel portion, right? You should really know that by heart. That one's easy, hopefully. But the other thing you cannot predict, right? There's a lot of material. So I'm not going to test you on that material. But I think notes could be helpful just so that you feel more comfortable. So if you're willing to bring notes in the sense that the notes that you have written, since we don't have a book here, right? Actually, you're welcome to bring the papers also if you want, but they're not going to help you. I guarantee that the papers that are not going to help you. In fact, they're going to hurt you. So I don't recommend you bring any papers. But if you want, and if you decide to bring 3 pieces of notes, A4, I will not enforce that you're not supposed to bring notes. Okay? So you're free to bring 3 pieces if you would like to. Okay? Who wants to bring notes? Like these 3 pieces? Just to get a poll. It's okay. I mean, I would bring notes, for example, because I would do them while I'm preparing for the exam, actually. Okay. Any questions? Thoughts? Are we over time? Not yet. You still have time for 2 questions. Now this is the time to ask for the exam. So I think what we will do is we will probably have a review session next week. Or is it next week? Yeah, sometime next week is probably a good idea, right? That's 1 week before the exam. We don't want to do it the day before the exam, probably. So yeah, so you can bring questions to that review session. Okay. Yes? Sure. Irrelevant. Okay, this discussion is over. Let's take the irrelevant question for 1 minute.
Okay, let's say you invented something like can you license your ideas?
Well, if you patent them, yeah, you can then, right? But if you don't patent them, if you just write a paper about it, if you release the idea to the public, then you cannot do anything about it. So most of the work I do, for example, I don't patent. I don't believe that any university should be patenting. As a result, these are all public, in the public domain. But that's not the philosophy of everyone in the end. So you can actually make a lot of money out of this. In fact, there are some places that aggressively sue other places to make that money. I'm not going to go into that right now, but... But yeah, there have been actually academic works that are published, and they patented it, and other people either license them. That's the nice way of getting access to it. You actually pay for licensing. But if you don't license it, and if you use a similar idea, and if someone finds that out, and if they sue you, that someone who finds out may make a lot of money. And you may lose some money. Yeah. Okay, I guess have a good weekend.